Hello and welcome to the course Object Tracking using Python and OpenCV. My name is Jones Granatier and I will teach all the lectures in this course. Tracking means locating an object in successive frames of a video. And now let's look at some of the projects that you are going to implement step by step. We can see this window here, where we can track the objects or the runners. The goal is to select any runner that you want, and the algorithm will track them until the end of the race. We will also use the webcam. Take a look here that we are tracking this pen. Even when the pen is in front of my face, the algorithm still tracking the object. Another example using the webcam, we can click in the object we want to track and see that this route is generated, so you can monitor where the object is going. We can also see this other visualization, which is useful to see the exact route that the object is going. We will also implement a different kind of tracking in which we can see people walking, and instead of have the bounding box around the object, we can fill the objects with colors to see where they are moving. During implementations, we will use all these tracking algorithms that are available in the OpenCV library. There are 12 algorithms in total. You will learn the basic intuition about each one, and then we will implement and test using OpenCV and the PyCharm IDE. It's important to emphasize that the goal of the course is to be as practical as possible, so don't expect too much from the theory since you are going to learn only the basic aspects of each one. The purpose of showing all these algorithms is for you to have a view that different algorithms can be used according to the types of applications, so you can choose the best ones according to the problem you are trying to solve. We will perform some tests and compare the results. Now let's take a quick look at some object tracking applications. This first image shows some examples related to traffic control, such as tracing the route here, tracking pedestrians here, calculating the distance between vehicles, and so on. This type of technique has many applications that can be used in self-driving cars. This other image shows the tracking of soccer players, so a heat map can be generated indicating the main locations that each player visited through the game. For example, if you are monitoring a defensive player, he or she is expected to occupy that part of the field here. If you are monitoring an offensive player, he or she is expected to occupy that part of the field here. An analysis can be made to check if the players are fulfilling his or her role during the game. This other image can indicate the recognition and tracking of people. First, the system can detect faces, then it can check if it is a certain person you are looking for, and then you can track him or her. There are many commercial applications that can be developed using tracking. That's it for this lecture. In the next one, you will have some theoretical background about the algorithms, and right after, we will move on to the practical implementations. I hope you have a great course and enjoy the content. See you next time! Hello and welcome to this lecture where you are going to learn the differences between object tracking and object detection. Sometimes both terms are used as if they were the same, but there is a very important difference, mainly regarding to how the implementation of the algorithms was made. In general, tracking algorithms are much faster than detection algorithms because to track an object, the algorithm already knows what it looks like in order to track it in the next frames of the video. For example, let's suppose that the goal is to track the runner to the end of the track. In this frame here, we already have basic information about the object, and when you are in this position here, where I am pointing the mouse, we can use this information about the features of the object, and also the algorithms can detect a kind of pattern that indicates the direction and speed of the object. The runner is following the track from left to right, so the algorithm already knows that in the next frame of the video, the person will be here. In short, this information is used to predict the location of the object in the next frame. For this reason, tracking algorithms are faster because they use existing data, whereas a detection algorithm would have to be executed from scratch frame by frame, without reusing data. It would take a longer time to execute. On the other hand, tracking algorithms can have a little difficulty in tracking objects that change position drastically. For example, if in the next frame the person appears below here instead of following the straight line. In this situation, it will be difficult for the algorithm to follow the object. If there is a video composed of 100 frames, a detection algorithm will run 100 times, once for each frame. On the other hand, a tracking algorithm will detect the object only in the first frame, and then it will use that information until the end of the video. When you start working with some algorithms, it is common to have some problems. For example, in this image here, see that the bounding box moves away from the object, and it can happen when the speed is very high and the algorithm loses contact with the object. In this other image here, see that the leg of the runner does not appear very well due to the speed. Therefore, the algorithm can also have difficulties in tracking the objects, and the bounding box was placed higher. To solve this type of problem, you can try different algorithms. Some of them are suitable for faster videos. Later in this course, you will learn a lot of algorithms, and we will be able to perform some tests related to this issue. Another solution to this problem is to use a detection algorithm again to reset the tracking algorithm. For example, when this bounding box here loses the object, we run a detection algorithm again to put the bounding box in this position here again, so that the tracking starts again. Later, we will implement tracking plus detection. Finally, a tracking algorithm can adapt to small variations in the images in the videos. For example, in these cases where the person puts his or her hands in front of the face, a face recognition algorithm would probably not recognize the faces, while a tracking algorithm would still be executing correctly. It happens because a tracking algorithm considers the location and appearance of the object in the previous frame. In the previous frame, the algorithm identifies that this person here did not have his hands in front of his face. And when the person puts the hands in front of the face, the algorithm will continue tracking. In other words, the algorithm already has the information for the right part of the face here, which was obtained from the previous frame. This animation shows the differences between tracking and detection. As you can read here, tracking preserves the object's identity. Once the algorithm starts tracking, the object is treated as a single entity. For example, look at this orange point where I'm pointing the mouse. It has the same color from the beginning to the end of the trace. It's the same object and it indicates where the object is going. On the other hand, the detection only analyzes each frame of the video. It's not possible to follow the path of the object. That's all for this lecture, and in the next one you will start learning the basic intuition about some tracking algorithms. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about tracking algorithms. First, you will understand the intuition, and then we will implement them step by step using Python and OpenCV library. We have this image here, where the goal is to select the runner and track him to the end of the track. There are two important concepts that are used in almost all tracking algorithms. The first is called motion model, which is a combination of location and speed in previous frames. So, based on location plus speed, it is possible to predict the next location of the object in the next frame of the video. We have the current frame here, with the bounding box around the object, and the prediction will indicate that in the next frame, the object will be in that part of the track where I am pointing the mouse. The second concept is the appearance model, which, as the name suggests, is responsible for storing the object's appearance or the shape to search for locations close to where the object will be in the next frame, the nearby positions. Some searches will be performed around the object where I am pointing the mouse to predict the next location and speed. Let's suppose that in the next frame, a car appears in this position. The appearance model will check that the appearance of a car is totally different from the appearance of a person. They have different shapes, so the algorithm will continue tracking only the person. Here we have a summary of these two concepts. The motion model predicts the approximate location of the object. The appearance model adjusts the location to provide a more accurate location based on the appearance of the object. And in general, algorithms use both techniques together, the motion model plus the appearance model. The purpose of a tracking algorithm is to classify a rectangular region as an object or the background of the image, which is everything in the image that has no relation to the object that we are tracking. For example, in this image, several bounding boxes will be created here, here, and here. And the algorithm will receive an image patch as input. This is a terminology that represents information about the pixels of the images. And it will return a value in the range from 0 to 1 that represents a probability of the area being the object or the background of the image. The closer to 1, the more likely it is to be classified as the object. On the other hand, the closer to 0, the more likely it is to be classified as the background. Each one of these rectangles is an image patch that will be sent to the algorithm, and then we can get the probabilities. For example, 10% here, 80% here, and 10% here. As the person is in the central part of the track, we have a higher probability in the middle box, which is the real direction of the object and the prediction of the algorithm. So, in short, the algorithm will receive as inputs the image patch of the surrounding possible positions that the object could go and will generate a probability for each one of them. And the highest value will be the selected location of the object in the next frame of the video. Tracking algorithms can be developed using two machine learning techniques, online learning and offline learning. Most algorithms use the first approach. They are trained in real time and at runtime. The training starts when the algorithm is executed, and all mathematical calculations are done during execution. On the other hand, thousands of images are needed to train an offline classifier. For example, to track cats and dogs, it would take thousands of images of cats and dogs. So the algorithm can learn from the images before tracking them. Online learning is faster, and training starts when you select the object you want to track. In the next lectures, we will implement so it will be easier to understand. And that's all for this basic content about object tracking algorithms. And in the next lecture, you will start learning the intuition of some tracking algorithms. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about two tracking algorithms, and the first one is boosting, as you can read here. It is a slow algorithm, does not work very well, it's not so efficient, and it is based on the hard cascade classifier with the AdaBoost algorithm. This is the algorithm used for detecting faces and objects with OpenCV. It is one of the simplest techniques for detecting objects. Training is online, meaning that learning happens when you want to track an object. It uses the concept of positive and negative images. The positive image is the object you want to track, while the negative image is the background. For example, in this image here, you must create the initial bounding box by selecting the object to be tracked, which is the positive image, and the rest of the image is the negative part that does not have the object. For example, the house, the wall, the people here, and so on. In short, 1 if it is the object, and 0 if it is the background. We can read the definition here. the initial bounding box, this blue bounding box here, is the positive example, and the rest of the image is treated as the background, the negative examples. We can consider that this image is the first frame of the video, and this one is the second frame, in which the person has his back turned. See that we still have the blue bounding box that indicates the object, and two other orange boxes were created, which are the negative examples. Of course, more boxes will be generated and not just two. The next step to continue tracking the object is to generate the probabilities for each one, and the one with the highest value will be considered as the positive bounding box. Here, the blue box had the highest probability compared to the others. It's similar to this slide here, where the goal is to select nearby bounding boxes and return probabilities to each one of them. And that's all for the basic intuition about boosting. The next one is MIL, Multiple Instance Learning, and generally it has better results than boosting. The training is quite similar, and see that in this image we have the positive examples in green. Let's suppose you selected only this region of the image where I am pointing the mouse. Then the algorithm itself creates other bounding boxes to increase the image area. As you can see here, there are two additional bounding boxes. Instead of using just one positive example, there are several others that are created automatically. On the other hand, negative examples, these red rectangles here, are also created far from the positive examples. In short, rather than just considering the object's current location as a single positive example, the algorithm looks for positions around the current location to generate several potential positive examples. Since there are three positive examples, the probability of selecting them is greater than if we had only one positive example. Again, as for boosting, probabilities will also be generated and only one bounding box will be selected to continue tracking the object. This other image shows this process in more detail, where you can see the positive examples that are around the face of the person. Shift to the right and shift to the left. When a prediction is made, only one of these regions will be selected, the one with the highest probability. We can also look at the negative examples that are far from the positive examples, with these parts of the shoulder of the person. The advantage of this algorithm, if compared to boosting, is that even if the object's current location is not found exactly, if we use these other bounding boxes here, we can still tracking the object. And that's all for this basic intuition about these two algorithms. And in the next lecture, you are going to understand the intuition of some more tracking algorithms. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about two other tracking algorithms. The first one is KCF, kernel correlation filters, which is a fast algorithm. However, it doesn't perform very well, especially in fast videos. And one of the most common problems is when the bounding box loses the object, as you can see here and here. KCF is an extension of MIL algorithm that presents some improvements and considers that in the MIL algorithm, there are many overlapping regions, as you can see here. One box can be created above others. So, KCF aims to solve this problem. So, this image shows an example of how it works. We have here the first frame, which is the initialization or the definition of the object to be detected. When working with videos, we use the first frame to select the object we want to track. Let's assume that we selected this red frame here. For example, the goal is to track this face. So, the algorithm applies a concept called particle filter, as you can read here, and two more large bounding boxes are created to cover a larger part of the image. Here, the blue one, and here the green one. Next, from frame 2 to frame 3, the larger rectangle is used, the green one, and some mathematical calculations are made to adjust the frame in the central part of the face. As you can read here, the filter is updated. Then, from frame 4 to frame 5, the blue filter is updated to the center position of the face. Then, in the next frame, the same process is also made, now considering the red bounding box. After finishing the first update of all filters, see that the size of the larger filter has decreased slightly, the green one. See here in the original image that the border is next to this frame at the background, and here the position is quite different. So it was adjusted to the object. On the other side, you can see that the bounding box has been moved, here where I am pointing the mouse. The goal of the algorithm is to make several adjustments in these bounding boxes in order to circle the objects and be able to detect it. The larger frames are important to detect changes in the scale or the size of the object. For example, if in one frame the object is smaller and in the next frame the object increases in size, like a person approaching the camera. Now let's go to the basic understanding of the CSRT algorithm, which means discriminative correlation filter with channel and spatial reliability. It is more accurate than KCF, but is slower. This image shows the steps of the algorithm. In the first box here, we select the object we want to track, for example, only the person's head. See here this term patch, which is widely used in computer vision and is related to the information that was selected from the image, information about the pixels of the image. Then, in step number 2, a discriminative filter is created and the HOG, histogram of oriented gradients technique, will be used, and it will extract the most important information from the image and discards everything else. HOG will also identify the edges and corners of the image to discover the shape. For example, The head is shaped like a circle. In the third step, a random Markov test is applied, which is a mathematical concept, to predict the next image. See here that we have the same shape as the image, as if it were the person's next movement. In this step, probabilities will be generated to indicate the person's movement. For example, if the person turns his face to the other side, in this part here, that the prediction will be made in order to verify if the movement is of this person so that the algorithm continues tracking. Finally, in step number 4, a confidence map is used. In the image, we have only the object with a mask, and at the end, we have the complete object to be tracked. As you have noticed, this is a more complex algorithm that uses several computer graphics techniques, and the purpose of this lecture is only to present an overview. If you want to know more details, you can read this article for more information. In the next lecture, you are going to learn some more algorithms. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about 4 more tracking algorithms. The first is MedianFlow, which is not suitable for fast-moving objects or objects that change their appearance quickly. For example, if in one frame the object is far from the camera and in the next frame the object is too close to the camera. The main concept of the algorithm is that it tracks the object in forwards and backwards directions and measures the differences between these two trajectories. For example, in this image, we have the previous frame and the posterior frame. To know the next location the object will be, the algorithm calculates the difference between them. So, we know if the object is following the trajectory correctly. The algorithm is not suitable for objects that change appearance, according to this definition here, because of this calculation of similarity between frames. If here, where I am pointing the mouse, the runner changes its trajectory upwards towards the grass, the differences between the trajectories will be too large and it will not be possible to continue tracking. Based on this calculation, it is possible to predict tracking failures, or when the object leaves its position. In this example, you can identify if a runner is going out of his or her lane and is invading someone else's lane. This image shows how the algorithm works. We have the previous frame, t-1, the current frame, letter T here, and the arrows indicate the direction of the next movement. This other image shows the calculation of the median, which is a statistical concept, to calculate the differences between frames. If the difference of the median is small, the object is heading in the same direction. On the other hand, if the difference of the median is big, the object has changed direction. This is why this algorithm is called MedianFlow, because we are calculating the direction of median values. The next algorithm is TLD, Tracking Learning Detection. This diagram shows the structure of the algorithm, which is composed of 3 parts: tracking, learning, and detection according to its name. The first step is to start tracking the object, and while the object is being tracked, the data is sent to the learning process, so it adapts to tracking. While the algorithm is learning, it is online learning, the object detection process is improved, and the detection data is sent back to the learning process. When tracking fails, the algorithm tries to learn from its errors and sends the data to try to detect the object again. We are not going to see mathematical details, as the goal of the course is just to show a general overview of the algorithms. The next algorithm is MOSSE, Minimum Output Sum of Squared Error, which is one of the fastest but not so accurate. It's a good option if you need tracking speed and don't care so much about quality. The algorithm is robust to lighting variations. For example, if the light is on in the first frames and the light is off in the others. It's robust to scale. If the object is near or far from the camera, it is also robust to pose. For example, in the first frame, the person is facing the camera, and in the next frames, the person has his or her back to the camera, or when the person puts the hand in front of the face. In order to identify these changes in the environment, the algorithm uses a mathematical concept called correlation filters. This image shows how the algorithm works. In the first frame of the video, you select the face or the object you want to track. It is the initialization phase. See that the image is quite dark. And in the next frame, when we increase the light, the algorithm continues tracking the person's face. Frame 150 and frame 250. This red point indicates the center of the detection. And here we can see more information. We have the inputs, which is the object, the application of the correlation filter, and the output with the result of the object that was tracked. We can see only this center point here and here. Finally, the last algorithm is Goturn, which means generic object tracking using regression networks, which was trained using offline learning. This is the only algorithm with this feature we have seen so far. So it was trained using datasets composed of thousands of videos. It is based on deep learning and convolutional neural networks, which is a type of neural network widely used for image classification. Here we can see the architecture of the algorithm, which starts by the definition of the object you want to track. As we can see here, this image is sent to 5 convolution layers and 3 fully connected layers, so that we get a prediction of the object's location. The neural network returns a bounding box, as you can see here, with the position of where the object is in the next frame. Don't worry about understanding neural networks, because as I mentioned before, the goal of the course is just to show you the basics of each algorithm, and you can access the additional materials if you want to know more. Goturn doesn't have very good results because we need to track objects like the ones the algorithm was trained. For example, it will not be able to track fingers because it has trained with hand images. So, Before using it, you need to check the objects that the algorithm has been trained on. Of course, you need to perform some tests to see if the algorithm will perform good in your application. Finally, we have a summary of some of the algorithms. CSRT has the best performance, but is the slowest. KCF is not very good regarding quality, however, it is a very fast algorithm. On the other hand, MOSSE is the fastest of all. It is important to know these features of the algorithms for you to choose the best one according to the type of application you are developing. There are some applications where you need a lot of precision and speed is not so that important, so you can use CSRT. There are also some applications where the quality is not as important as speed, so you can use KCF or MOSSE. In the next lecture, we are going to start the implementations. See you there! Hello and welcome to this lecture, where I'm going to show you how you can install Anaconda and PyCharm on your own machine, since all examples will be implemented using both tools. You can access the Anaconda website, as you can see here. Let's click this option here. Then you can download it according to your operating system. We can see that it's possible to download for Windows, Mac, and also Linux. When you click this button, an installation file will be downloaded, and you must run it and follow the instructions. I'm not going to show you this process step by step, because it's basically following the instructions on the screen. In case you don't know Anaconda, it is one of the most used tools for programming in Python, especially for working with artificial intelligence and data science. The advantage is that several AI-specific libraries are already installed, and it is also possible to create environments with different versions of Python. For example, one environment using Python 2 and another environment using Python 3, and one environment does not influence the other. The next step is to install PyCharm, as you can see here, which is an IDE for working with Python. Let's click Downloads. Let's choose the community version, which is the free version. When you click this link, an installation file will be downloaded and you must run it and follow the instructions. Again, I'm not going to show you the process step by step because it's basically following the instructions on the screen. After installing it, you can open PyCharm, create this button here, New Project. Then you can select the location where you are going to save the project. For example, in my case, tracking, let's keep this option, New Environment using Conda. Select Python version, for example, 3.9, and then let's create this last button here. It will take some minutes to create the new project. You may see this screen here. In this left part, we can access all the files, and in the center part is where we are going to type the code. Now we need to install OpenCV library in order to have access to the tracking algorithms. We can create this button here, terminal, and let's type pip install OpenCV Python, press enter. We can see here that it is downloading the library and also installing some dependencies. Now we need to install another library. Let's type again pip install OpenCV contrib Python. We need this contrib package to have access to the tracking algorithms. Let's press enter again. We can see that it is downloading and installing the packages. Now we can perform a test just to make sure the installation was done successfully. Let's click in the name of the project, New Python File. Let's call this first file test OpenCV. Let's type import CV2, which means the library we have just installed. Let's type cv2.version. We can click run test OpenCV. No error was returned, so it means that the installation was done successfully. We can just print the version of OpenCV we are using. Let's run this code again. See that we have version 4.5.4. And in the next lecture, we are going to start implementing the algorithms. See you there! Hello and welcome to this lecture where we are going to start the implementation of tracking algorithms using OpenCV library. Just a reminder that last lecture we created this file test OpenCV just to make sure that the library was successfully installed. Now let's create a new file. I will click New Python File. And the name of the file will be single tracking. The first goal is to select and track only one object. Let's import the libraries. Import CV2. This is the OpenCV library. Import sys to have access to some functions of the operational system. From random import randint to generate random numbers. Now I will create the first variable, tracker type, in the format of a list. When we open and close brackets, we are defining a list in Python. And the goal is to define here the name of each one of the algorithms. The first one is the boosting. The next one, MIL, KCF, the next one, TLD, MedianFlow, MOSSE, and finally CSRT. This is the algorithms that we saw last lectures. And we are going to use this list to define the algorithm that we are going to use. Let's create another variable, tracker type. This first one, I will change the name for tracker types. And in this other variable, we are going to select one of these algorithms. Let's access, for example, tracker types in position 0. Let's print tracker type. We can run this code just to perform the first test. See that when we put number 0, we get the name, which is boosting. Indexes in Python starts from 0. Boosting is the algorithm 0. MIL is the algorithm number 1. KCF algorithm number 2, and so on. Let's put here 3. Run this code again. See that the result is TLD. Position 0, 1, 2, 3. We are going to use both variables in order to indicate the algorithm we are going to perform the tests. Let's implement an if statement. If tracker type equals boosting, then we are going to create the object. I will create this other variable, tracker equals CV2. Let's access this package, legacy dot tracker boosting underline create. This is the way we can create each one of the algorithms. We can print the tracker, but first let's just change it here to position 0, which is the boosting algorithm. Let's run this code. See here that we have this information, tracker boosting, and these letters here indicate that the object was successfully created. So now we have a boosting tracker in this variable here. This letter represents the address that the object is occupying in the memory of the operational system. Now we need to perform other if statements to create the other algorithms. If tracker type equals MIL, then the tracker will be equal to CV2 legacy dot tracker MIL create if tracker type equals KCF, then the tracker will be equal to CV2 legacy tracker KCF create. You can see that we are always accessing the same package. If tracker type equals the next one, TLD, then the tracker will be equal to CV2 legacy tracker TLD create the next one, if tracker type equals MedianFlow, then the tracker will be equal to CV2 legacy tracker MedianFlow create if tracker type equals the next one is the MOSSE algorithm, which is the fastest, then the tracker will be equal to CV2 legacy tracker MOSSE create, and finally let's move on to the last algorithm, if tracker type equals CSRT, then tracker equals CV2 legacy tracker CSRT create. And just to make sure that all objects will be created, let's test one by one. The first one is the boosting. The next one, MIL. The information here about the object means that it was successfully created. The next one, KCF. We can see this error message because here we need capital letter. That's the first one here, tracker. And let's correct for the other algorithms. Let's run this code again. Now the object was successfully created. The next one, number 3, TLD. Number 4, MedianFlow. Number 5, the MOSSE algorithm. And finally, number 6, CSRT. We can see here the message indicating that the object was created. This is the first step to implement object tracking. We are creating different objects according to the algorithm we want to perform the tests. And in the next lecture, we will continue the implementation. See you there! Hello and welcome to this lecture where we are going to continue the implementation of single tracking. Just a reminder that last lecture we implemented these codes to select the algorithm we want to use. And in this lecture, we are going to read the video that we are going to use as example, and then we will select the object that we want to track. I will create a new folder here, new directory. I will call the name of the folder will be videos, and you can access the course materials and copy and paste this file race.mp4. Let's click OK here. Inside this folder, we will store all the videos that we are going to use in this course. You can see the video here. The goal is to select the objects or the runners, and then we are going to track the runners until the end of the lanes. And the first step is to load the video. I will create a new variable, video, cv2.video capture. This is an OpenCV class to load videos. And now we just need to specify the path. Videos, it is the name of the folder with V in capital, race.mp4. Now we can just check if the video was correctly loaded. If not, video is opened. If it wasn't possible to load the video, then we can print an error message. For example, error while loading the video. And then we can just type sys.exit to finish the execution of this code. Sys is this import that we made in last lecture. We can just run this code to perform the first test. We can see here the name of the trackers. We can also put these two prints in comments. For example, if we change the name here to an invalid name, see that we have this message, error while loading the video. If this message is not shown, it means that the video was correctly loaded. Now we need to get the first frame of the video to select the object we want to track. I will create two new variables, OK and frame. The OK variable will indicate if we could load the first frame of the video. On the other hand, the frame variable will store the first frame of the video. Now we can type video.read. It will read the first frame. We can also type here, if not OK. If we couldn't load the first frame of the video, we can print again an error message. Error while loading the frame. And then we can just type sys.exit. We can print this variable here, OK. It will return true or false. True if we could get the first frame, and false if there is one error while loading the frame. Let's run this code. See that true was returned here. So it means that we could load the first frame of the video. Now we will define another variable, bbox, which means bounding box. This variable will store the positions of the object in the first frame. And to select the object, an OpenCV function, which is select ROY. And we will send here the first frame. ROI means region of interest. Now we can run this code again. See that a new window was opened here with the first frame of the video, the first position. And we can see some messages here. Select a ROI and then press space or enter button. Cancel the selection by pressing C button. If you want to cancel, we can just type letter C. We can see that the process was finished. Let's run this code again. Now we can select the object. For example, we can just draw the bounding box in order to select the object we want to track in the first frame. This is very important when working with tracking algorithms, that when you have a video, first you need to select the object in the first frame. If you click outside the bounding box, you can select another object, and to confirm the selection, we can press space or enter. For example, I will press in my keyboard space. See that the process has finished. Because actually this code is only selecting the object. We are not tracking the object yet. And we can also print this variable bbox. Let's run again. I will select the runner, press enter. See here that some positions were returned. The first is the x-axis, the second, the y-axis. It means the coordinates of the bounding box. And here we have the size of the bounding box. Let's run this code again. For example, if I click in this part here at the beginning of the image, let's select this region here, press enter. See that position X is pixel number 4 and position Y is pixel number 3. It's at the beginning of the image. And see here that these other values are lower than the other ones because we have a smaller bounding box. Let's run this code again and select almost the whole image here. We have this big bounding box. Take a look at the positions, X and Y axis, and this is the size of the bounding box, the width and the height. So in short, this variable here will store the position of the object we want to track. Now we can recreate the OK variable. Let's call the tracker.init, and I will send here the frame. This is the first frame of the video, and also the bbox variable. Now we are initializing the algorithm. Take a look here that the tracker that we are going to use is number 6, which is CSRT. We can change to boosting, which was the first one you learned the intuition. So now we will create a boosting object. We will use this algorithm to track the object. So in this part here, we are initializing the boosting algorithm, and we need to send the first frame and also the position of the object we want to track. We can print OK here. Let's run these codes. Select the runner, press enter. We have here the information about the bounding box, and this message true indicates that the tracker was successfully initialized. Finally, we will define another variable, colors, equals, let's call the function we imported before, randint. We will generate random numbers between 0 and 255. Randint 0, 255, and finally randint 0, 255. Let's print this new variable, colors. Run this code again. We need to select the objects. See here that we have these values, which will be used to define the color of the bounding box. As we are using a random function, every time we run this code, we will have a different result. See that these values are different from the others, and we are defining 3 values because the pixels of the images are composed of 3 channels. One channel for the color red, one channel for the color G, and one channel for the color B. This is the RGB format. Just to better understand, we can use these 3 values in this RGB calculator. For example, we can type 17, the first number that was generated in channel R, 105 in channel G, and 165 in channel B. We can see this color here that was randomly generated. This is the RGB format. However, OpenCV works in the format BGR. The first channel is blue, the second is G, and the third channel is R. So, to get the color that will be generated considering these numbers, we need to change the order of the values. For example, R is 165, G is 105, and B is 17. We have this color here. So, these numbers will create a brown bounding box, and we are going to define these random colors because in next lectures we are going to implement multi-tracking, so we can track more than one object in a single video, and each one of them will have a different color. And in the next lecture, we are going to finish the single tracking implementation, and we will also see the results. See you there! Hello and welcome to this lecture, where we are going to finish the implementation of single tracking. Just a reminder that in the last lectures, we created this code to select the algorithm we are going to use. Then we defined the bounding box or the bbox variable, which is responsible for selecting the object that we want to track, which is in the first frame of the video. Now we need to go through each one of the frames of the video to continue tracking the objects until the end. We can implement a while loop, while true. I will redefine the OK variable and also the frame video.read. Every time we call this read function, we will move on to the next frame of the video. Take a look here that in this part, we call the read function, so we have access to the first frame of the video to select the object we want to track. And when we put this code inside this while loop, we are going through each one of the frames. First, we get the first frame, then the second, the third, the fourth, and so on. Let's implement an if statement. If not OK, if it wasn't possible to read the next frame of the video, it means that the video has ended. So we can just break the execution of the while loop. This code is used to stop execution when the video ends. In this part of the code, we are initializing the algorithm with the first frame and the first position of the object. And every time we read a new frame, we need to update the location of the bounding box, because in the next frames of the video, the object will be in a different position. So we can recreate both variables, OK, and bbox equals tracker dot update, and we just need to send the frame. And this is not the first frame. This is the second, the third, the fourth, according to the size of the video. We use the first frame just to initialize. And after the initialization of the algorithm, we need to update the location. We can also take a look at this variable, OK, and bbox. Let's run this code. I will select the runner, press enter, and we can take a look here at some information. We have here the first position of the object. This is the initial bounding box that we selected using the selectRoy function. And after processing every frame of the video, we are updating the position of the object. This is the first position, x and y axis, and this is the second position in the second frame of the video, in the third frame of the video, in the fourth frame of the video, and so on. See that these values here are not changed because they are the size of the bounding box, and it keeps the same size until the end of the video. And we can take a look here at the message. It means that the object could be tracked, and this is the new position of the object every each one of the frames. And here is the last position of the object. We can also print the OK variable here just to see the value equals false. Let's run this code again. Select the runner, press enter. We can see the results here, but we just need to put the OK variable after reading the frame. Let's run again. Select the runner, press enter, and let's wait until it finishes processing all the video. At the end, we can see false, which indicates that we couldn't read any frame anymore. So it means that the algorithm could process all the video. And then the break will be executed to stop the while loop. Let's put these two prints in comments. And now let's see the results in the video. If OK equals true, if we could read and track the object, we will draw a rectangle to see the results. Let's create the variables x, y, w, and h equals, in the format of a list, let's convert to int v. I will create this variable v now for v in bbox. It means we are accessing this variable, which is composed of the x and y axis and also the size of the bounding box. and we are copying each one of the values to each one of these variables. For example, this first value will be copied to variable x, the second to variable y, the third to variable w, and the fourth to variable h. We can just see these results, print x, y, w, and h. Run this code again. Let's select the runner, and we can see here the results. We are just copying each one of the values of the bounding box to each one of these variables here. And now we can draw the rectangle on the image. CV2 dot rectangle. We can use this OpenCV function. The first parameter is the frame. Just a reminder that every time we run this while loop, we are getting the next, and the next frame. So we will put the rectangle in each one of them. The next parameter is the first position, x and y, which means the initial position of the bounding box. The next parameter is the final position of the bounding box. So we can put here x plus w, which is the width of the bounding box. This number here, we are just adding this value plus this value. And then y plus h. We are adding this value plus this other value here. The next parameter is the colors variable. As we saw before, we are defining random colors to draw the bounding box. The next two parameters are related to the size of the bounding box. For example, 2 and 1. In some seconds, we are going to perform some tests changing these values. If it is not okay, if we couldn't update the bounding box with the next position, we will print a message. CV2 put text frame. Let's type tracking failure when the algorithm was unable to track the object. The other parameter is the position where we are going to print the message. The next one, CV2 font Hershey simplex. This is the type of the letter, the size of the letter, the color in the BGR format 00255, and finally the thickness of the letter, number 2. And finally, CV2 IMShow to see the results. Tracking, this is the name of the window, and let's put here the frame. If CV2 dot wait key, this OpenCV function is used when we want to type a specific key. For example, we can type here this symbol 0xFF. This is a hexadecimal code. If it is equal to 27, then we can break the execution. This number 27 means the ESC key in your keyboard. So when you press ESC, we are going to break the while loop so the window will be closed. Now let's test again. Run. Let's select the runner. Press enter. And we can see here that the tracking is already working. Of course, we can see a problem here because we are using the boosting algorithm. We can press ESC in the keyboards to close the window. Let's first try with the MIL algorithm, which is index number 1. Run this code again. Let's select the runner, press enter. See that every time we run, we have a different color here because the colors were defined randomly. And see that we have a problem because we selected the yellow runner and the algorithm started tracking this other runner. And it happens because these two first algorithms aren't so good. As we saw in the intuition lectures, they are the most simplest algorithms to track objects. So the results won't be good in all scenarios. Now we can perform some tests using these parameters. For example, let's change here from 2 to 10, just to see the results. Select the runner, press enter. As you can see, this is the size of the bounding box. Let's move again to number 2. And actually, this last parameter we don't need to specify because it is the type of the line. For example, if you want a dashed line or a solid line. So we don't need to worry about the last parameter. And the same for this one here, we can just erase. And we cannot see this message tracking failure because the bounding box was generated. Of course, it wasn't around the objects, but the algorithm could still generate in the bounding box. We get this message only if we can't update the next location of the object. In the next lecture, we will perform some other tests and we'll check when we will get tracking failure. Finally, we can just put another message on the frame. I will copy and paste this code here. Let's put here the name of the algorithm, tracker type, the positions 120, and we can keep the other parameters. Now let's run this code again. Select the runner, press enter. We can see here at the top of the video the name of the algorithm. So it is nice to see the name of the algorithm in order to check the results. And in the next lecture, we will perform some tests using all algorithms. See you there! Hello and welcome to this lecture, where we are going to perform tests using all algorithms and compare the results. First, let's test the boosting algorithms. As you learned in the intuition lectures, this is one of the simplest algorithms, so the results are not so good. Let's select the object we want to track, press enter. We can see that after only some seconds, the bounding box is outside the object. In other words, we have that problem that the algorithm loses the object, so it hasn't good results in this video. Let's move on to the next algorithm, which is MIL, the one we tested last lecture. Let's select the runner, press enter. We can see that it is better than boosting. It can track the object, but there is a problem, as we saw last lecture, that after some frames, it loses the objects, and it seems it is tracking that other runner and not the one we selected. Let's try KCF number 2. Run this code. Let's select the object, press enter. We can see that it is a very fast algorithm according to what you learn in the intuition lectures, and it has good results better than boosting and mill in this type of video. Let's move on to the next one, which is TLD. Run this code. Select the object, press enter. You can see this message, tracking failure. And the algorithm couldn't track the object. It lost the object at the beginning, and you can see here some other bounding boxes. The algorithm hasn't good results. And we can take a look at the code here. That message, tracking failure, is shown when the algorithm couldn't generate the bounding box. You could see that after some time, some other bounding boxes are generated at the video, which indicates that the bounding box was updated, but not in the correct location. In this execution here, we can see that the algorithm wasn't able to generate any bounding box. So it has terrible results considering this case study. The interesting points about knowing the basic intuition about these algorithms is that you can know better the way each one behave. So you need to test them all in order to choose the best one according to your type of application. Maybe in this scenario, TLD has terrible results, but in the scenario that you are working, it may be the best results. So it's a matter of testing the algorithms. Now let's move on to the next one, which is MedianFlow. Let's create the bounding box, press enter. We can see that it hasn't good results, again, tracking failure, and some other bounding boxes were generated outside the object. Let's try to define another bounding box, a smaller bounding box here, press enter. No improvements in the results using this algorithm. You can see that it is a fast algorithm. Now let's move on to the next one, which is the MOSSE algorithm. Select the runner, press enter. We couldn't even generate the bounding box in the first frames of the video. We got the message tracking failure. Let's try another test. For example, selecting a smaller bounding box, press enter. We can see that the bounding box was generated, but this video is too fast for this algorithm. So we won't get good results. And finally, let's perform the test using the best algorithm of all these ones here, the CSRT. Let's select the runner, press enter. You can see that it is a slower algorithm if compared to the others, but we can see that it can track the runner until the end of the video. Let's change again to the mill algorithm, and I will perform the last test. I will try to track only the heads of this person here. Press enter. We cannot track. The algorithm was enabled and we can see the message tracking failure. Let's change again to CSRT. Let's select the heads. And in this part here, even when the heads were very close, the algorithm could correctly track this head here. So it has very good results. And again, when you are developing your own application, I encourage you to test all the algorithms so you can choose the best one according to the type of application you are developing. and I encourage you to download other videos and try to test these algorithms. And in the next lecture, we will implement multi-tracking. So we will be able to select more than one object to track in the same video. See you there! Hello and welcome to this lecture where we are going to implement multiple tracking. If you remember last lectures, we implemented the single tracking that the goal is to select only one object. And in this implementation, we will allow the user to select as many objects he or she wants. We can press Ask to quit this window, and I will create a new file, new Python file, multiple tracking, and I will copy this code of the last example, paste it here. And in this lecture, we will implement some improvements in this part here. Remember that we need to put here the number to get the name of the algorithm. We will create a new function to be easier, so the code will be more organized. Let's create the function create tracker by name. It will receive as a parameter the tracker type. Let's implement an if statement. If tracker type, which is this parameter here, we will send the name of the algorithm and we will return the object. If it is equal to tracker types, now we are accessing this list here in position 0, then let's create the variable tracker cv2 dot legacy dot tracker boosting create, the same code we had before. If tracker type equals, let's access the list in position 1, which means MIL algorithm, then tracker will be equal to cv2 legacy tracker mil create. I have already typed all this code. We can see here the definition of the KCF, TLD, MedianFlow, MOSSE and CSRT. And if we send an invalid name, we can implement this else statement. Tracker will be equal to none, and let's print a message invalid name, and let's also print the available list of trackers. Let's type here available trackers, and let's go through each one of the trackers. For T in tracker types, we are going through this list here to show the name of the available algorithms to the user. I will print T, which is the name of the tracker. This for loop is going through each one of the elements of the list, and it is copying each one of the names to the variable T, then we print it. And finally, let's return the object, returned tracker. Let's perform some tests. I will print create tracker by name. Let's send here CSRT. We can run this code. We can see that the object was returned. So it means that this function is returning the tracker correctly. I will copy and paste this code. And if we type an invalid name here, for example, CSRT8, I will just put this in comments, run this code, see here the message invalid name, and then we can see the available trackers, boosting, mill, KCF, and so on. And at the end, none is returned because we are associating the tracker with an invalid object. And this is the first part, just an improvement on the code we implemented before. In the next lecture, we are going to continue the implementation. See you there! Hello and welcome to this lecture, where we are going to continue the implementation of multiple tracking. Just a reminder that last lecture, we just did some improvements on the single tracking code. Now I will copy this part here, where we are loading the video, copy, and paste it here. We can put this print in comment. We are just loading the video. And then we will define two new variables. The first one, bboxes, an empty list, and colors, again, an empty lists. In the single tracking example, we have only one bounding box, and now we need to select more than one bounding box in the first frame of the video. So we are going to store all the bounding boxes and the corresponding colors in these new variables. I will define a while loop, while true. Let's create the bbox variable cv2.select ROI in order to select the region of interest. Let's type here multi-tracker. It is the name of the window, and we also need to specify the first frame of the video. Let's create these variables here. OK, and frame video.read. We are accessing this variable here. We are copying to the frame variable the first frame of the video. After selecting the bounding box, we will access the bboxes variable dot append bbox. We are adding the bounding box to this list here. We also need to access the colors variable, and let's define the random numbers in order to have different colors. Randint 0255, randint 0255, randint 0255. We are generating a different color for each one of the bounding boxes. Now we need to define the key to be pressed on the keyboard to interrupt the execution of this while loop after we select all objects that we want to track. I will create a new variable, key equals cv2 wait key 0. This parameter 0 is expecting a key from the keyboard, and we also need this hexadecimal code. And now we can just check if key equals 113. This is the code for ladder key, which means quit. So when we press quit, we will interrupt the execution of the while loop. Then we can just break the code. To be easier to test this code, let's print two messages. Press K to quit and start tracking, and another print. Press any other key to select the next object. Now let's run this code. We have that same messages, so we can open this window. Let's suppose we want to track this runner. We select him, and then we press space or enter to confirm the selection. Let's press enter. Now we can see the new messages. Press key to quit and start tracking, and press any other key to select the next object. If we press key, see that the execution is interrupted. So it means we entered this if statement here and the while loop is stopped. Let's run again. I will select the runner, press enter, and now we can press any other key to select the next object. You can press any other letter, for example, A, B, C, D, P, and so on. I will press letter P. We can see the message again. Select Roy and then press space or enter. I will select this other runner, press enter. Now we can see this message again. Let's suppose we want to select another object, so we can press any other key. For example, letter A. We select the other, enter, and when we finish selecting all the objects we want to track, we can press key. And then the while loop is interrupted. To see the bounding boxes, we can print B boxes, and we can also print the colors of each one of them. Let's run. Again, I will select the first runner, press enter. I will type letter P to select the next runner, press enter, letter P or any other key to select other objects. I will select this one here, press enter, then I will press letter Q, and then we can see the results. 3 bounding boxes with 3 corresponding RGB colors. And this is the code needed to select each one of the objects we want to track. We need 3 bounding boxes and 3 different colors. And in the next lecture, we will finish the implementation. See you there! Hello and welcome to this lecture, where we are going to finish the implementation of multiple tracking. Just a reminder that in last lecture, we implemented this while loop in order to select the objects that we want to track. We will have, as a result, a list of several bounding boxes with the corresponding colors. Now I will create the tracker type variable, which will be the name of the algorithm. Let's perform this test with CSRT algorithm, which is one with bad results. I will create another variable, multi-tracker equals CV2, and there is this other class from OpenCV, which is multi-tracker create. We can take a look here that before we were creating each one of the algorithms, and now as we can have more than one tracker, we can use multi-tracker create. Now we need to go through the bounding box for bbox. In bboxes, we are going through this list of the selected objects, and we need to add the trackers. Multi-tracker dot add, and let's call our function create tracker by name, and let's send here tracker type, which in this example is the CSRT algorithm. Let's suppose we select 3 objects to track. Each one of them will be tracked using the same algorithm. And if you want, you can send different algorithms and not the same as we are implementing here. We also need to send here the frame which is the first frame of the video, in order to initialize the algorithms. And also, we will send here the bounding box. We are going through each one of the objects and adding them to the multi-tracker. Now, we can go through each one of the frames of the video. While video is open, when we have the next frame of the video, we will execute these codes. Let's create the variables, OK, and frame. Just a reminder again that this variable here is the first frame of the video that is used only to select the position of the objects that we want to track. And this other variable here will receive each one of the next frames. Let's type here video.read. If not OK, if it wasn't possible to read the next frame, we can break this loop. Let's recreate. OK, and boxes. Let's call multitracker.update, and let's send here the frame. This is exactly the same we had before. First, we need to initialize the algorithm with the initial positions of the object, and then we just update according to the next frames. Let's create a for loop for I and new box, two variables I am creating now in enumerate boxes. This for loop is going through each one of the boxes, because if we select 3 objects to track, we will have 3 bounding boxes as result. And now we need to go through each one of these updated bounding boxes in order to draw the rectangle. And the enumerate function is used to give indexes for the boxes. For example, in the first execution of the for loop, we will get here the first bounding box, and it has index 0. Then we will have the second bounding box with index 1, the third bounding box with index 2. We will use the I variable to access this other variable here, to get the colors of each bounding box. Now we can create x, y, w, h equals the same code we had implemented before. We are going through each one of the bounding boxes and put each one of the values in each one of these variables here. For v in new box. Now we can draw the rectangle. CV2, rectangle. The first parameter is the frame, the initial position of the bounding box, the final position, x plus w, y plus h. And now we are going to use the colors variable, and we will send variable I here. The last parameter is the size of the bounding box, which will be equal to 2. After the last part, CV2 I am show. Let's type here the title of the window, multi-tracker, the frame, and if CV2 wait key 1 e 0xff equals 27, which is the ask key. So when you press this key in your keyboard, the execution will be interrupted. We just break the loop. Now let's run this code and perform the test. I will select the first runner, press enter. Now we can see this message here. press any other key to select the next object. You can press any other key, for example, letter P. I will select this other runner, press Enter. Then we can select another one, press any other key, and I will select the last one here. Press Enter, and now we can press Q to quit and start tracking. We can see that one error was returned. Module CV2 has no attributes multi-tracker create, because we need to access this other package called legacy. Let's run again, and I will select the runners, the second one, and the third one. Press Enter and Q, and finally we can see the results using CSRT algorithm. We can see that the algorithm is performing well. It's possible to track the three objects at the same time. Let's wait until the end of the race. As you can see, it is quite slow because we are executing the algorithms using three objects. And this is how you can perform multiple tracking using OpenCV. See you in the next lecture. Hello and welcome to this lecture, where we are going to implement the Goturn algorithm using OpenCV. In last lectures, we can see that we implemented all others algorithms and it's missing Goturn, and we will implement in a different file, as you can see here, because there is a small difference on the implementation. As you learned in the intuition lectures, this algorithm uses convolutional neural networks to perform tracking, so we need to load some additional files. I will click here, paste, see that two files will be copied here, goturn.proto.txt and goturn.cafemodel. You can get both files in the course materials. Now we are going to implement an if statement just to make sure these files are in the same folder as the source code here. If not, os.path is file. Now we can type the name of the file, goturn.cafemodel, and in case you don't know, CAMShift is a deep learning framework. So the neural network was trained using this framework. This file contains the weights of the neural network, and this other file here, we can open it. It has the data about the neural network. For example, we can see here the convolution layers. Don't worry about understanding the structure of the neural network, because this is not the goal of the course. You just need to load both files in order to work with this algorithm. And os path is file. This function is used to check if the file exists in the folder. Now let's type Goturn proto.txt. If we can't load both files, let's print a message, error loading the network files. And then we can just type sysexit to interrupt the execution. We can run this file. No error was returned because both of them are here in the same folder as the source code. We can try to change the name here, run this code again. Now we get the error message, error loading the network files. Now let's create the tracker, which will be equal to CV2 legacy, the same code we implemented before. Tracker, Goturn, create. Now we can run this code. See that one error was returned because for this specific algorithm, we don't need to use the legacy package. We can just keep CV2 tracker Goturn create. Let's run it again. See that no error was returned. And from now, we can use exactly the same code we implemented before. The only difference between this algorithm and the others is that you need both files here. I will just paste this code here. It is the same we implemented before. First, we load the video, then we get the first frame. We have the definition of the ROI, the region of interest, or in other words, the object that we want to track. We initialize the algorithm, sending the first frame and also the bounding box of the first position of the object. Here we have the definition of the random color, and inside the while loop we have the same code as before. We load the next frame of the video. If we cannot load the next frame, so we break the execution of the while loop. We update the bounding box. If we can update it, then we just draw the rectangle. If we cannot update, we have the tracking failure message. We put the text with the name of the algorithm in the top part of the video. And finally, we just show the results. This code is exactly the same for the other algorithms. Now let's run the algorithm, select the object we want to track, and as you can see, we don't have good results using Goturn with OpenCV, because as you learn in the intuition lectures, you need to be sure about the objects that this algorithm was trained with, because as you learned, it was trained using offline learning. So a dataset with thousands of videos was used to train the algorithm. So you need to make sure that the objects you want to track are in this dataset that the algorithm was trained. Otherwise, you won't get good results. And in the next lecture, we will continue the implementations. See you there! Hello and welcome to this lecture where we are going to implement a detection algorithm, and right after we will combine the tracking algorithm with a detection algorithm. And just to better understand what we are going to implement, I will run the single tracking file. Let's choose here the MOSSE algorithm. Let's run this code, select the object we want to track, press enter, and you will see that after some time, the bounding box loses the object. We can try to run this code again. Let's select this other runner here, only the top part of the body. We can see that after some time, the bounding box is far from the object. And when this situation happens, we can run a detection algorithm to try to get the object again. Because if you are still running the tracking algorithm, probably you won't get good results, since the algorithm is losing the object. So we can combine both techniques. When the tracking algorithm loses the object, we will run a detection algorithm in order to get the object again. And in this first lecture, we will implement a detection algorithm and then we will combine both. I will create a new Python file, test detection. Let's import the libraries, import CV2, OpenCV. I will create the image variable, CV2 IMRead, and let's create a new folder here, directory. I will call images. I will paste the test image here. You can get this image in the course materials. People.jpg. We can open this image. We can see a lot of people here, and the goal is to detect the full body of each one of them. In this example about the combination of both algorithms, we are not going to use the same video as before. We will use a different one. Now we can just type here the name of the image, the full path, images.people.jpg. I will paste a new folder here, which is the Cascade folder, and we can see here some XML files. For example, full body, hair cascade eye, hair cascade frontal face, lower body, and upper body. These are files that were already trained in order to detect the parts of the body of people. For example, only the upper bounds, the part of the head, the lower bounds, the part of the legs, only the frontal face, the eyes, and the full body. And this is the most common technique in OpenCV to detect objects. And these files are already trained to detect these parts of the body. And you don't need to worry about how they were generated, since this is not the goal of the course. We are going to use the full body file to detect the people here. Now we need to create our detector, which will be equal to CV2 cascade classifier, and we just need to send here the name of the file, cascade directory, and fullbody.xml. We can just run this code just to make sure no error was returned. Then we can convert the image to grayscale, because when working with cascade classifier, this OpenCV technique, it is recommended to convert this image to grayscale. So we can create another variable, image gray equals CV2 CVT color. Let's send here the original image, and color BGR to gray. To see the results, we can type IMShow. Let's put here the name of the window, people, and image gray. At the end, let's type wait key, parameter 0. It means that the window will be waiting until we press a key. Let's run this code. We can see this window here. If we don't type CV2 wait key, we won't be able to see this grayscale image. We can type any key, and then the window will be closed. Now we can use our detector to detect the full body of the people. Let's create the detections variable, detector, and to detect objects, we can call this function detect multi-scale, and we just need to send image gray. We can print the results, print detections. We can put these two lines in comments. Let's run this code again. see that some bounding boxes were returned with the position of where the full body of the people were detected. We can also print length detections to see how many objects were detected. The result is 9. Let's open the image. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 people here. So it seems that the algorithm is able to detect all people. Now we can draw the bounding box in the image. Just a reminder that the two first values are related to the position, the x-axis and the y-axis, where the object was found in the image, while the last two values are the width and the height of the bounding box that was detected. Now we can implement a for loop for x, y, width, and height in detections. We can print all these variables just to see the results. I will put this in comments. Let's run the code. See that we are going through each one of the bounding boxes and just copying the values to each one of the variables. Now we can draw the rectangle. CV2 dot rectangle, the first parameter, the image. See that we are drawing the rectangle in the original image, in the RGB image, and we are using the grayscale image just to run the algorithm. The second parameter is the initial point. The third parameter is the end point of the bounding box. I will keep the same values as here. The next one is the color, 0, 255, and 0. And the last one is the size of the bounding box. Now we can remove the comment here to see the results. And we also need to show the image. CV2, I am show detections. And here we are going to send the image. It's important to emphasize that we are drawing the bounding box on the original image. And after visualizing the image, we can destroy all windows to release the memory. Let's run again. We can open the window. We can see some points here, which is the initial point of the bounding box of each one of the people. This is the x and y axis, but we need to draw the bounding box. So we just need to add the values. X plus width, y plus age. Now let's run again. Open the window and we can see the results. The algorithm was able to draw the bounding box for each one of the people. We just have some problem here that only the lag was detected. And if you want to improve the results, you can check the documentation of this function detect multi-scale in order to see more parameters. It's not the goal of this lecture to go into these details. The goal is just to show you how you can use a detection algorithm. And in the next lecture, we are going to combine the detection algorithm with the tracking algorithm. See you there! Hello and welcome to this lecture where we are going to start the implementation of the combination of the tracking algorithm with the detection algorithm. Just a reminder that last lecture you understood how to use the hard cascade detector to detect the full body of people. Now let's create a new file, Python file. The name of this file will be detection tracking. Let's import the libraries. Import CV2, import sys, and from random import randint. Now let's create the tracker equals CV2 legacy, and I will use tracker CSRT. You can use the one you want. We are going to use CSRT because, as we saw before, it has the best results. Now we can go to the single tracking, and I will just copy this code here to load the video, paste it, and let's paste the new video that we are going to use. Click here on paste, walking, the name of the file, and you can get this video in the course materials. Here is the video that we are going to use in this case study. We can see a lot of people walking on the street, and the goal is to select a specific person and track the person until the end of the video. And if we use a tracking algorithm, after some frames, the tracking algorithm will lose the object, and then we are going to use the detection algorithm to try to get the object again. Then we can restart the tracking algorithm. Let's just change the name here, walking.avi. Let's run this code. No error was returned, so the video was loaded correctly, and also we could get the first frame of the video. Now we will create the cascade detector, which will be equal to CV2 cascade classifier, and let's send here the full path of the file, full body.xml. As you saw in the video, we have the full body of people, so we can use this file here. If you are working with eye tracking or only tracking the frontal face of people, you can use these other cascade files. I will create a new function, def detect. It won't receive any parameter. Let's implement a while loop, while true, OK, and frame video.read. See here that we are reading the next frame of the video. Now we will get the frame, which is the first image, and let's convert to grayscale. As you learned in last lecture, to work with the cascade classifier, it is recommended to convert the RGB image to grayscale image. We will implement a similar code we implemented before. CVT color frame CV2 color BGR to gray. After we convert, we can get the detections equals cascade, and let's call detect multi scale, and let's send here the grayscale image. Now we need to go through the bounding box, exactly the same we did here. See that we first get the detections, and then we need to go through each one of the detections or the bounding boxes. For x, y, width, and height in detections, I will draw the rectangle frame. Take a look here that we are converting the image to grayscale. We are detecting the full body in the grayscale image, but we are going to show the results in the RGB image. Let's put here the first point, the last point, x plus width, y plus height, the color of the bounding box 00255, and the size 2. Let's show the results. CV2, I am show, detection, and let's put the frame here. After that, we can visualize the results. CV2, wait key, and after we press a key, let's destroy all windows to release the memory. Now we can perform the first test using this function. Let's call it detect, and I will run this code. We can take a look at some images. This is the second frame of the video, since we have here this code to read the first frame, and the hair cascade wasn't able to detect the full body in this frame. We can press any key, then we move on to the next frame of the video. The algorithm is detecting this rock here as if it were a person, but now we can see that the algorithm could detect the full body of this person here. We can move on to the next frames. We can see that the algorithm can detect other people, and you can press enter, or you can press any other key on your keyboard, and you can see that the algorithm is detecting the full body of people. Of course, there are some errors here, but it won't be a problem for our case study. I will click this button here to stop the execution, and the goal of this function is to detect the first person who appears in the first frame of the video. As we can see here in the single tracking, when we run this code, we need to select the bounding box in order to start tracking. Then, when we press enter, the algorithm starts executing. But in this other case study that we are implementing, the goal is to select the first person that the algorithm could detect. So, we are not going to use this function here, the select row, because when you use this function, a window will appear and you need to select the object by yourself. But in this other case study, we will automatically select the first body that appears in the video, and in order to do that, we can implement an if statement. If x greater than 0, if a detection was found, then we can just print hair cascade detection, and then we can return the bounding box x, y, width, and height. The difference is that in single tracking, we select the object and we have here the bounding box according to our selection. Now, we will return the bounding box according to the first frame of the video, or in other words, according to the first object that was detected. Now we can create the bounding box here, and then we can just print the B box. Let's run this code. We can click here, stop and rerun. See that we have the detection, hair cascade detection, and we have only the first bounding box. This is the X and Y positions, and here we can see the size of the object that was detected. And in the next lecture, we will initialize our tracker according to this bounding box here, and then we will combine both algorithms, the detection algorithms and the tracking algorithm. See you there! Hello and welcome to this lecture, where we are going to finish the combination of a detection algorithm with a tracking algorithm. Just a reminder that last lecture we implemented this function that will read the first frame of the video, and then we will get the bounding box of a person. When we call this function, we copy to this variable the return of the function with the position of the bounding box. And now we are going to go through each one of the frames of the videos in order to run the tracking algorithm. The code will be quite similar to the one we implemented before. While true, OK, and frame video.read to read the next frame of the video. If not OK, then we finish the execution of the while loop if there is no frame to read when we reach the end of the video. Now let's create again the OK variable and the bounding box equals tracker.update, and let's send the next frame. We can see here that we defined the tracker, the CSRT algorithm. And in this line of code, we are updating the location or the position of the bounding box. Just a reminder that we are using this function to get the object instead of using the select row function. The algorithm itself will select the object to track. If OK, if we could update the bounding box, let's create X and Y variable WH equals int V. Let's go through each one of the values of the bounding box for V in B box. Now we can draw the rectangle, CV2, rectangle, frame, position X and Y, X plus W, Y plus H. Let's put here the colors, but we need to define this variable. We will use random colors. Let's just paste this code here. We can put this bounding box in comments. And we also need to initialize the tracker. Tracker.init. Let's send the first frame and also the bounding box, the initial position that will be got from this function detect here. If we are not able to track the object, we can print that message, tracking failure, and we are going to implement some additional codes in this part here. But first, let's just try how the tracking is working. CV2 IAMShow. Let's put here the name of the window, tracking, and frame. Let's create the key variable, CV2 wait key, parameter 1. The window will wait for a special key, and then if key equals 27, which means the ask key, then we just break the while loop to close the window. Here we just delete this symbol. We can run this code, there is one error. Object has no attribute ints because here it's missing letter I, tracker.init. Let's perform the first test. Run this code. Let's open the window. See that the rock was detected by the hair cascade. You can see that it is updating the bounding box. It means that tracking is working correctly. However, as this rock is not moving, we cannot see the updates. And we can make some improvements to not detect this rock as it were a person. We can set a parameter to detect multi-scale function. Let's type here mean size, which is the mean size of the object. Let's type here 60 by 60. This is the minimum size of an object to be detected. As the size of the rock is lower than this value, then we will detect another object. Let's run the detector again. We can take a look that now we can't detect the person. But after some time, we can see that we lose the bounding box. And when it happens, we will run the detection algorithm again to choose another person in order to continue tracking. We will implement this part in this else statement. If it is not okay to continue tracking the object, we will send this message, tracking failure, and another message. We will execute the hair cascade detector. And now we will recreate the bounding box just calling our detect function. We will call this function. It will read the next frame of the video and will return the position of the full body of a person in order to restart the detector. Now we can recreate our tracker cv2.legacy tracker. I will choose another one, for example, tracker MOSSE create. You could also use CSRT or any one you want. In this code, we are executing two tracking algorithms. At the beginning of the execution, we are using CSRT, and when we have a tracking failure, we will use the MOSSE algorithm. And then we need to initialize tracker.init frame and bbox. We are initializing the tracking algorithm again according to the new bounding box. Before executing the first test, let's remove this comment here just to show the first object that was detected. Run detection tracking, and here we can take a look at the first objects in the first frame of the video. And then we can see that the algorithm started tracking, but see that it has lost the object, but we don't have here that failure message because the bounding box is being generated. Of course, it is not correct. It is not tracking any object, but we are not executing this part of the code here. And it happens because of the size of the bounding box. As we can see here again, the bounding box is very big and the person is not so big as the bounding box. We can also take a look at our test detection file. Let's run it, and we can see that the bounding box are also big. It means that we are sending to the tracking algorithm all this information about the background. so the tracking algorithm will have some difficulties in tracking the objects since the bounding box is too big. And it is a problem of this file here, the full body XML. So it is not so accurate to detect the full body of people. It would be better if the bounding box was smaller around the object and not so big with this information about the background. And the tracking algorithms will use the information about the background to track the objects. Let's run this code again. We can see here the size of the bounding box. See that we have this background information here, that it is part of the object, as we can see here, because the bounding box is considering the pixels about the person and also the pixels about the background. So it would be better if we had a more accurate hard cascade to detect full body of people. To solve this problem, we can implement this code in a different way. Instead of using the detect function in the first frame, we can use the function we were using before. cv2.select ROY, and let's send the frame. I will put this other line in comments. Now we will be able to see this message, and I will put all this part in comments just to see if we will get this tracking failure message. Let's run this code again. Now we need to select the object we want to track. Before, we had a big bounding box, and now we can create a bounding box according to the size of the person. Let's press enter. See here that the tracking has already started, and let's wait until we see the message tracking failure. See that the algorithm loses the object. Now we have this message tracking failure, and the tracking algorithm is not being executing anymore because there was this failure and we couldn't update the bounding box. So now we can run this code in order to call the function to detect the object. Let's remove the comments. Let's run the code again. The first step is to select the object we want to track. Let's run it. And here we can see the video. So the algorithm is continue tracking the objects. And see here that only one error was returned, and it happened because I changed here to the CSRT algorithm. So we are initializing with CSRT, and when we have a tracking failure error, we are executing again CSRT. We can try now with the MOSSE algorithm as we had before. Let's run this code again. I will select the first object we want to track. The goal is to track people. Let's run this code. We can see the video. Here, the ROY selector with the first frame. Now let's wait until the algorithm returns a tracking failure. At this part here, this is the new object. It was executed once, similar to the other algorithm. And you can test with other algorithms. I will run this code again. I will select a bigger bounding box. Let's try to run again. And the results will depend on this first bounding box. Of course, after we have a tracking failure error, we will have a big bounding box because we are using the hard cascade. See here that we have this big bounding box. And again, only one error was returned. Let's try again, and I will select this other person here, press enter, and let's see the results. One error was returned here, the same as before, and after the algorithm finishes the execution. This is how you can combine both algorithms. When you have a tracking failure, you can run the detection algorithm again. As I said before, this hard cascade here, full body, is generating quite big bounding boxes. It would be more interesting and the results would be better if we had the bounding box at the same size of the objects. And in the next lectures, we will move on to more advanced tracking algorithms. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about the Meanshift algorithm, which uses space analysis to find the maximum of a density function. The bold texts here are the main concepts of the algorithm, and now let's understand how it basically works. It determines the weight of nearby points or pixels based on average calculation using colors. Let's suppose that in this animation there are 4 pixels, 1, 2, 3, and 4, and you select this white pixel here to track. So the algorithm will move towards this white pixel. As you can see, the pixels are moved until they reach this area here where you want to track. This is the density function. When the number of pixels is greater, it is basically an approximation of the pixels according to the features of the initial object. This other image shows another example, where you can see the arrow moving towards this white part here, which might be what we want to track. So this is the density function. There is another representation of the algorithm. There are a set of points on the left side and some windows or circles here. These 3 points. The algorithm needs to move these windows or circles to these areas here where I am pointing the mouse. The algorithm will approximate these red pixels to this image. In other words, we are going to move to the area of maximum pixel density, where there are more pixels than in other parts of the image. It will be moved to this red part at the top where the density is higher. Below, we have the representation with these 3 bars, and this is the biggest because there are more pixels here. Let's count, for example, 1, 2, 3, 4, 5, 6, 7 pixels, so the bar is higher than the others. In this other one, 1, 2, 3, 4, 5, 6 pixels, so the bar is smaller than this one here. And finally, in this point here, there are only 1 pixel, so the bar is smaller than the others. So this is the density function that counts the number of pixels in each one of these windows here. The size of the bars indicates the density, as you can read here, the data point density. The goal is to bring these points closer to this image, which is equivalent to this one above. And the letters PDF stand for probability density function, which is the mathematical calculation used in Meanshift. We can consider this image here as the current frame of the video and this image here as the next frame. A confidence map based on probabilities will be created to approximate the frames, so that the algorithm can identify where the target object is. Larger bars here are related to greater probabilities, while smaller bars indicate less probability of the object being in this position here. In short, the object we want to track is in this central part, where the density or number of pixels is greater. This other animation shows how the approximation works. There are more pixels in the center, and the algorithm goes here where the object is located. This is the basic intuition about Meanshift, and in the next lecture we will start the implementations. See you there! Hello and welcome to this lecture, where we are going to start the implementation of the Meanshift algorithm. We are back to the PyCharm project. Let's create a new Python file. The name of this file will be Meanshift. Let's import the libraries, import CV2, and we will install another library. We can click here in terminal and let's type pip install imutils. Press enter. We can see here that the installation was successfully done, and this is a library to work with videos in Python. We will use it in some seconds. Now we can import a class from this new library from imutils.video import video stream. In this case study, we are not going to load a video from this folder here as we did before. We will load the videos from the webcam. Now we can create the capture variable video stream, this new class that we have just imported. The first parameter is the source, which will be equal to 0, which means the webcam. In case you have more cameras installed on your computer, the webcam will be camera 0 and the other cameras will be camera 1, camera 2, camera 3, and so on. And now we are going to start capturing the images from the webcam. I will import another library here, import time, and let's type here time.sleep1, which means that we are going to wait 1 second before we start capturing the images from the webcam. And we need this code because when we are capturing videos from the webcam, it needs some seconds in order to adapt to the environment. For example, maybe you have already seen that when you turn on the webcam, it takes 1 or 2 seconds to adapt to the light conditions. For example, even if you are in a light environment, when you open the webcam, in the first milliseconds, the image will be quite dark because the webcam is adapting to the environment. So we are going to use these codes to wait 1 second to give time to the webcam adapt to the lighting conditions. And we are going to select the object we want to track after this process. In short, we are giving 1 second to the webcam adapt to the lighting conditions of the environment. Now we can recreate the cap variable CV2 video capture. Again, we will put 0, which means that we are getting the images from the webcam. If you remember the other lectures, here we typed the path of the video. So the code is the same to read video files or to get the video from the webcam. I will create 2 new variables, OK, and frame equals cap.read to get the first frame of the video or the first frame when the webcam is initialized. Just a reminder that this variable OK will tell us if the connection was made successfully. We can just print OK just to see if we can get the images from the webcam. Let's run this code. We can see this message here. It means we could get the video from the webcam. Now I will create the bbox variable cv2.selectROY. We are going to select the object from the webcam. We will put here the first frame of the video. After selecting the bounding box, let's create x, y, width, and height variables equals bbox. We can create another variable. I will call it as tracking window, which is the object we want to track. And it will be equal to each one of these variables here. Let's print the track window just to see the results. Now we can run this code. We can see the first frame of the video. I am holding a pen, and the goal will be to track this pen. We can select a small bounding box here, just with this part. And after pressing space or enter, we can see that we have the same messages as before. We get as a result the bounding box of the initial object that we want to track. We can see here position X, position Y, and the size of the bounding box, just that small part of the pen. Now we need to create a new image which will be equal to only this part of the image, only the object or the part of the pen I selected before, the object we want to track. So we can create a new variable called ROY, which means region of interest, and we can access our frame. This is the initial frame that was read here, and now we can type the following code: y until y plus h, this is the initial position of the image, x plus w. We are using these two variables here to get the initial point of the bounding box, and these other points here, which are related to the size of the object we selected, to get only that part of the image. We can visualize the results. CV2, I am show the title of the window, ROY, and let's put here the new variable, and CV2, wait key, number 0, the window will be opened until we press a key on the keyboard. Now let's run this code again. I will select the bounding box, a small one here, press enter, and we can see this other window here with just of this part of the image that I have just selected. We first need to get this initial part in order to send to the algorithm, so it will track only this part of the pen. And this is the first part of the implementation, where we give time to the webcam to adapt to the lightning conditions. We select the object we want to track using select ROI from OpenCV, and then we get only the part of the image that we want to track. And in the next lecture, we will continue the implementation. See you there! Hello and welcome to this lecture, where we are going to continue the implementation of the Meanshift tracking algorithm. Just a recap, we can run this code. Then we can get the bounding box. For example, we can select the pen, press enter, and we can see here the ROI, or the region of interest. This is the object we want to track, which is the track window. And now we need to perform some pre-processing on this ROI image. I will put these two lines in comments. And as you know, this image is in the RGB format. Of course, in OpenCV, the order of the channels are different, so we have a BGR image. And we need to convert this RGB or BGR image to another format, which is the HSV. It is another color representation or another color space. And if you want to know more details about the color spaces, you can follow this first link here, where you can find more information about color spaces. For example, they are used according to the available light in the environment, the way the objects in the scene reflect light, the way the light reacts with an animal's eyes, and the way received light is processed. Different color spaces are used according to these 4 features here, and we can take a look at the RGB color space, which is the one used in computers, and it is considered the default color space. And we can take a look at the HSV color space, and instead of have the red, green, and blue channel, we have the hue, the saturation, and the value. As the Meanshift algorithm is based on colors, we need to convert the image from the RGB format to the HSV format, because this is how Meanshift algorithm was implemented. So we can create a new variable, HSV ROI equals CV2 CVT color. Let's send here the ROI, or the object we want to track, CV2 color BGR to HSV. And just to compare the results of each one of the color spaces, we can show the window, CV2 IM show, let's type here, ROI HSV, HSV ROI, CV2 wait key. Let's run this code again, and so it will be easier to see the difference between the two color spaces. We can select the ROI again. Let's press enter, and now we can see the difference between the original one and the color changed from RGB to HSV. We can delete this comment here. Let's run again. Let's select the part of the pen again, press enter. Now we can see both color spaces, the original one, the RGB, and the same image converted to HSV. We can put this line in comments, and this is the first pre-processing step. We need to convert the object from RGB to HSV. Then we will need to perform these calculations here to approximate the number of pixels to these areas or to these bars. For example, this is the biggest one because there are more pixels in this window here. This is the second biggest because there are less pixels than this one here. And then we need to approximate these bars to the next frame of the video in order to keep tracking the object. We need to compare the previous frame with the next frame. And the next step now is to generate these bars. And the bars are called histogram, and you can follow this link to know more details. We can take a look at the theory here. The histogram is a graph or plot which gives you an overall idea about the intensity distribution of an image. For example, we are going to count the number of pixels according to the colors. For example, see that in this part of the image, we can see the brown color, and the number of brown pixels are higher than the number of this color here, near the C. So, the bar regarding the brown color is bigger than the bar regarding this other color, because the number of brown pixels are greater than the number of this white pixel here. And we can also take a look at this point here, which is a different color. But as this mountain is far from the camera, the color is quite different. And the number of pixels belonging to this color is smaller than the number of pixels belonging to this other brown color. So basically, the histogram will give us the number of pixels belonging to each one of the different colors of the image. Going back to this slide here, we can consider these points here as the brown color, these other points here as this other color here, and finally this other part here as this white color. So basically, in order to perform the calculations, the Meanshift algorithm will use the histogram with the number of pixels of each one of the colors of the image. So then we can compare these histograms with the histograms of the next frame of the video. If the algorithm can find similarities between both histograms, it means that it can keep tracking the object. This is how Meanshift finds similarity between the current and the next frame of the video. It will compare the histograms. Here you can find the OpenCV codes to get the histogram of the image. And now we are going to implement it. Let's go back to the PyCharm project. I will create another variable, ROI hist cv2.calcHist, and the first parameter is HSV_ROI. We are going to get the histogram regarding the ROI converted to HSV color space. The next parameter is the number of channels. We are going to use only one channel. If you want to know more details about the parameters, you can check this link here. For example, if the input image is in grayscale, the value is 0. So we are going to get the histogram considering a grayscale image. The next parameter is the mask image, and we need to set as none to find the histogram of full image. And as we need to get the histogram of the ROI, we need to put none here. We would use this parameter if we want to find the histogram of a particular region of the image. The next parameter is the hist size. This represents the bin count, which is the number of bars that will be generated, or the number of intervals. For example, in this image, there are about 20 bars. So that parameter would be equal to 20. We can type 180, which is the number of bars that will be generated, or the number of color intervals. And in the documentation of Meanshift algorithm, it is recommended to use this value. And the last parameter are the ranges. For example, the default value from 0 to 255, which is the RGB interval. And as we are working with HSV, the range will be from 0 to 180. So now we have the histogram of the ROI, and we can visualize a graph like this one here to show the number of pixels according to each one of the colors. To do that, we are going to use another library. I will click here in Terminal. Let's install Matplotlib, which is the default library to generate graphs in Python. We can see that the installation was done successfully. Now we can import this library. Import matplotlib pyplot_splt, and we can use matplotlib to generate the histogram. Let's type hist ROI, and I will define the same parameters. Then we can show the graph cv2 weight key 0. Let's run this code, and one error was returned here because this ROI variable is an image, so it is in a matrix format, and we need to convert in a vector format only one dimension to generate the histogram. Let's try to run this code again. The first step is to select the ROI, press enter, and we can see the result here, which is quite similar to that one in OpenCV documentation. We can see here the total amount of pixels regarding each one of the colors. Most of the values are in the range from 75 to 175, which are related to the yellow color according to the pen. In short, these are the most frequent colors. And take a look here that we are generating the histogram using the original image, so it is easier to see the results. Now we can put this code in comments. We are not going to visualize this graph anymore. It was used just to see the results. And the last step of this lecture, we will recreate ROI hist equal CV2 dot normalize. As we know, the values are in the range from 0 to 255, and we need to convert them in the range from 0 to 1, so it will be faster to process the algorithm. We are going to normalize the image. We are going to send here the ROI hist, again the ROI hist, the original interval 0 255, CV2 norm min max. This option will convert the values of the pixels in the range from 0 to 1. And in the next and last lecture, we are going to finally visualize the results. See you there! Hello and welcome to this lecture, where we are going to finish the implementation of the Meanshift algorithm. As you could see, this is a quite more complex algorithm if we compare to the others. We need to perform a lot of pre-processing, since selecting the bounding box, converting the image from RGB to HSV, and also generating and normalizing the histogram. Just a reminder that the histogram will be used to perform the comparison between the frames, so the algorithm will be able to track the object. Now we need to define another variable, parameters. As the name suggests, this variable will store the parameters of the Meanshift algorithm. And we will define two parameters, CV2. The first one is the term criteria EPS. Then we can type this bar, CV2 term criteria count. Now we need to define the values for each one of them. For the first one will be 10. We will copy number 10 to the first parameter, and the second parameter will be 1. This value will be copied to this other parameter, and we got this value from the documentation of OpenCV. We are using the default values. To start from this point here until get to this central point, the parameter simulates this flow until we get the object we want to track. The higher the value, more accurate the algorithm is. However, the higher the value, the slower the algorithm is. So, if you don't have good results with the algorithm, you can try to increase this value, so the tendency is that the results will be better. And regarding the second parameter, it indicates how sensible the algorithm is regarding changes in the object. For example, if in the first frame the object is close to the camera, and in the next frame the object is far from the camera, this parameter will control the movements the object can make during the execution of the algorithm. If you specify a big number here, the algorithm won't be able to detect the changes in the object. And similar to EPS, you may try some values according to the type of video you are working with. Now let's implement the while loop to go through each one of the frames of the webcam. I will create the variable OK and frame cap dot read. We are reading the next frame of the webcam, similar to what we implemented using videos. If OK equals true, if we can access the next frame of the video, then we will perform all the steps of the algorithm. The first one, we need to convert the frame that is coming from the webcam from RGB to HSV. CV2, CVT, color, frame, CV2, color, BGR to HSV. This is the first step because we need to put the current frame with the same format of our ROI. Just a reminder that we first select the object, then we convert to this color space. So we need to keep the same format. I will create another variable, dst CV2, and let's call an OpenCV function, calc back project, and I will send here HSV. It is the current frame. We are going to use only one channel. Now we will send here ROI hist. It is this variable here which contains information about the histogram of the object we want to track. So we are comparing the current frame with the object we want to track. It is this part here. We are comparing the original histogram of the object we are tracking with the current frame of the video. In short, this function will calculate the PDF, or in other words, the probability density function. And now we need to specify the other parameters, the interval 0 to 180, and the last parameter is the scale of the image. We will put 1 here, so we will keep the same scale of the image. We are not going to perform changes on the original image. And in case you want to know more detail about this OpenCV function, you can follow this link. Now we are going to call the Meanshift algorithm. I will recreate OK variable and also the track window, which will be equal to CV2 Meanshift, and we are going to send here dst, the calculation that is comparing the histogram of the object with the current frame. And then we need to specify here x, y, w, and h, which is the position of the object. We can take a look at these variables that were defined here, which are equal to the bounding box. So we are sending the position of the object. And finally, the last parameter is this variable we defined here, with the values for the EPS and the count parameters. This code is quite similar to this one here, tracker.update, where we are updating the position of the objects in the webcam. And this OK variable will tell us if the algorithm was able to update the position of the bounding box. Now we will recreate the variables x, y, w, and h equals track window. We are updating the position of the object. Now we can draw the rectangle CV2 dot rectangle frame, which is the image that is coming from the webcam, x, y, the initial position, x plus w, y plus h. The color of the bounding box, 0, 255, and 0, and the size of the bounding box equals 2. Now we can draw the image. I am show. Let's type here the name of the window, Meanshift tracking, the frame. If CV2 weight key equals 13, which means the ESC key on the keyboard, then we break the execution. And we had implemented this if here at the top. If we can continue reading the frames, then we can execute the Meanshift algorithm. Otherwise, if there is errors while reading the frames, we can just finish the execution of the while loop. At the end, CV2 destroy all windows and also cap.release to release the memory. Finally, let's perform the test. I will run this code. The first step is to select the bounding box. I will select this small one, press enter, and now we can see that the algorithm is already working. I can move the pen, and the algorithm is tracking the pen using Meanshift. Even when the pen is in front of my face, the algorithm is still tracking the pen. So we can see that we have good results. There are two problems with this algorithm. The first one, if I move the pen very quick, you can see that the algorithm cannot track it anymore. And if I move the pen again near the bounding box, we can still tracking the object. And the other problem is that if I put the pen near the camera, we can see that the algorithm has good results, but the size of the bounding box is exactly the same as the initial position. On the other hand, when I put the pen far from the camera, we can see that the bounding box keeps the same size. And we can implement an additional code. Let's type here CV2 I am show. I will put here DST, which is the result of the probability density function. And let's type here DST. Let's run the algorithm again. Let's select the bounding box, press enter, and we can see this other screen here, which is the probability density function. See that when I move the pen, we keep the aspect of the object, which is the probability density function, and we can visualize this type of results because the algorithm is based on colors. See that when I put the pen in front of my face, we can clearly see the pen. And even when I put the pen in the background of the video, it is possible to track and to see the difference between the objects and the other parts of the image. We know that the pen is yellow and my face has a different color, so we can see this contrast with my face and the object we want to track. This is another kind of visualization for this algorithm. It tries to simulate this part here, when we are calculating the density of the data points. And in the next lecture, you are going to learn another algorithm that will increase or decrease the size of the bounding box according to the position of the object. See you there! Hello and welcome to this quick lecture where you are going to learn the basic intuition about the CAMShift algorithm, which is an improvement on the Meanshift you learned before. We added these three letters, C, A, and M, which means continuously adaptive Meanshift. Last lecture, we performed some tests using Meanshift, and the bounding box was always the same size whether the object is near or far from the camera. If you remember the practical implementation, when we moved the pen, the size of the bounding box was always the same. The main feature of this new algorithm is that the bounding box will update according to the size of the object. If it is close to the camera, the bounding box will be larger, while the bounding box will be smaller if the object is far from the camera. It is a dynamic process which gives more quality for tracking. With respect to mathematics, it also uses average calculations like the Meanshift algorithm. This image shows how the algorithm works. We can see this red rectangle that is the execution of the Meanshift going through the image. When the region of interest is found, the yellow rectangle here, this circle will be created, so it will increase the size of the bounding box. See that in the first runs, the bounding box is small, and after increasing the size, the algorithm manages to select the entire face of the person, as we can see here. For this reason, it is possible to track objects far or close to the camera. If you want to know more details, you can follow each step of the algorithm, reading these messages that appear in each change of state. For example, Meanshift, first, second, and thirds, ROI for the ellipse generation, and so on. This is the basic intuition about CAMShift, and in the next lecture we will implement it and perform some tests to compare the results with the Meanshift algorithm. See you there! Hello and welcome to this lecture where we are going to run the CAMShift algorithm. And as you can see here, the source code is already implemented. We are not going to implement it step by step because it's quite similar to the Meanshift algorithm. We have a new import here, import numpy s and p, and all this code is the same we implemented before. We need to get the image or the object we want to track using the select ROI function. We extract only the object, convert from RGB to HSV, then we need to get the histogram and normalize it. Just a reminder that this algorithm is quite similar to the Meanshift, so we need to compare the histogram of the image or the histogram of the object we want to track with the histogram of each one of the frames that are coming from the webcam. Inside the while loop, we are accessing the frames that are coming from the webcam. We convert them to the HSV color format. Then we calculate the probability distribution function using the callback project. See here that we are sending as parameter the histogram of the object we want to track and also the current frame. There is one difference here. Instead of calling Meanshift, now we are calling CAMShift function, and the other parameters are the same. We just have a difference here instead of drawing the rectangle using cv2.rectangle as we implemented before, we are getting the points using cv2 box points that are the positions of the bounding box. We are converting to integer numbers using NumPy, and we are using polylines function from OpenCV. And we are creating a new image to draw the bounding box around the object. If you want to know more details about this function, you can follow this link here from the OpenCV documentation. Now let's run this code. The process is the same. First, we need to select the bounding box. I will draw a very small bounding box here. Press Enter. And we can see that the size of the bounding box is bigger than the one we defined at first, because this algorithm is dynamic. So the bounding box will increase and decrease the size according to the position of the object, if the object are far or close to the camera. See that the size of the bounding box has increased a little when the object is far from the camera. And when the object is close to the camera, the bounding box is a little bit smaller. And this algorithm has the same problem as the other one. When we move the object very quick, it loses the bounding box. So you need to perform some tests with the parameters according to the type of video that you are working with. And in the next lecture, you are going to learn the intuition about other tracking algorithm. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about another algorithm, which is optical flow, which considers the direction and speed of pixels. It is similar to the motion model you learned in the first lectures that indicates where the object will be in the next frame. It considers location plus speed in previous frames. For example, the farther the car is from the camera, the smaller the movement of the pixels is, because as the image is smaller, there are less pixels in the image. If the car is here at the ends of the image where I am pointing the mouse, its size will be much smaller and the amount of pixels will also be smaller. In other words, when the size of the car is smaller, there are fewer pixels to track. On the other hand, when the car is closer to the camera, the object is bigger and there are more pixels to be tracked. So, the movement of the pixels will be greater. In short, the closer the object is from the camera, the greater is the variation of the pixels. Like the Meanshift algorithm, optical flow also uses HSV color representation, as you can see in this image. Letter H, which means hue, is used to indicate the direction of the pixels, where they are moving. This arrow can point to the right, left, up, or down, while the S letter, the saturation, is used to indicate the speed of the pixels. If the object is moving slowly, the saturation will be low from frame to frame. On the other hand, if the object is moving quickly, the saturation will be high between frames. Finally, letter V here, the value, indicates the intensity of the colors. The closer the object is to the camera, the greater the intensity of the colors. The farther away the object is from the camera, the less intense the colors are. We can see the definitions here. H is used to indicate the direction of the pixels where each pixel is moving, and saturation, letter S, is used to indicate the speed of the pixels. Now we will take a look at the optical flow algorithm considering the sparse version. There are two versions of this algorithm, sparse and dense, and in this lecture we will focus only on the sparse version of the optical flow algorithm. Looking at this animation is easier to understand how the algorithm works. The more movements in the image, the bigger the arrows. They are closer to the camera. On the other hand, the less movements in the image, the smaller the arrows. They are farther from the camera. We can see this car here further away with a small arrow, and this other car close to the camera with a large arrow. We can see the same pattern here on the poles and on the roads. For example, small here and big here on the roads. In short, the closer to the camera, the more motion will be detected. To calculate how much the pixels are moving, we can use this equation at time t, the current frame, and at time t plus 1, the next frame. This calculation is related to the pixel intensity, the V-channel of the HSV representation. And here we can see that the pixel is moving to the left and with the intensity decreasing. This pixel is more intense than these two pixels here. Now we will see some mathematical calculations that are used in this algorithm. It is important to understand because we are going to use them in the implementation. Initially, the algorithm detects corners and edges to determine the orientation of the vectors using an algorithm called Harris corner detector. It is important to emphasize that in this step, the algorithm will select only some corners of the image and not the complete object. For example, see that in this car, where I am pointing the mouse, there is only one arrow and not a bounding box around the entire object. The algorithm will choose a corner of this image to track. The image will not be processed pixel by pixel. The algorithm will select only one corner of the object. Here you can see the equation considering x and y axis of the image and also the u and v parameters of the HSV matrix. These two parameters indicate the movements of the pixels, and letter I indicates the pixel intensity. The purpose of the algorithm is to find values for u and v to know the direction of the arrow. The arrows considering this image. Then we have the calculation of the matrix determinant, which is an algebra concept, according to this other equation, these words that here. And then we get the results in letter R. So the first step of the algorithm is to find the initial corners to start tracking. This symbol here indicates the highest value, and this other one indicates the second highest value. And don't worry about understanding these complex calculations. The idea is just to see the basic equations to be easier to understand the implementations. Researchers Shi and Tomasi modified the original equation and created a simplified version according to this other equation here. Instead of using the matrix, they use the calculation of the minimum between the highest value and the second highest value. Just a reminder that this calculation will predict if a pixel is a corner or edge of an object. This calculation is performed for all pixels and the computational cost is high. So OpenCV uses the concept of pyramids called KLT methods, Canate, Lucas, and Tomasi, the name of the researchers, which are three different methods combined, and it will analyze smaller images of the same frame. It is easier to understand by looking at this image. This bottom part is the whole image. Each little square is a pixel. We can count them. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6. 6 rows and 8 columns. Multiplying both values, 6 times 8, the result is 48 pixels. And we can take a look at this part here with 1, 2, 3, 4 and 1, 2, 3. 4 times 3 equals 12. So, from 48 pixels, the image has been reduced to only 12 pixels. And then, from 12 pixels, the image has been reduced to only 4 pixels. And finally, from 4 pixels, the image has been reduced to only 1 pixel. So the image is smaller and the calculation will be faster. On the left, we have the image at time t, and on the right, we have the image at time t plus 1, the current and the next frame of the video. After the image size is reduced, the optical flow is calculated from top to bottom, as you can see the arrows. And the goal is to find values for U and V that will indicate the direction of the arrows or the direction of the object. In short, first the image dimensions are reduced, and then the frames are compared using the reduced versions of the images. The process starts at I3, I2, I1, and finally I0, which is the number of layers to process the image. That's all for the basic intuition. In the next lecture, we will implement it using OpenCV, and then it will be easier to understand some of these concepts. See you there! Hello and welcome to this lecture, where we are going to start the implementation of the sparse optical flow algorithm. We are back to our PyCharm project, and I will create a new file, Python file, and the name will be Optical Flow Sparse 1. We are going to perform 2 tests using this algorithm. In the first one, we will get the initial corners regarding the first frame of the video, and in the second experiment, we will select the object that we want to track. Let's first import the libraries. Import NumPy, SNP, and also import CV2, which is OpenCV. I will create a new variable called cap CV2 video capture. We are going to read a video instead of using the webcam. I'm going to access the videos folder walking.avi. It is this file here that we have used to test other algorithms. And the first step is to define the parameters. I will create a new variable, parameters, Tomasi, and the name of the variable is related to this calculation here to get the R-score to generate the initial border and edges that were detected in the image. This is why it is important to understand this basic intuition about optical flow, because we need to use them in the implementation. We will define this variable in the format of a dictionary, and the first parameter is max corners equals 100. As the name suggests, it is the number of corners that you want to detect in the initial frame of the video. We are specifying 100 corners. The higher this value, the more objects the algorithm will track. After this lecture, you can play with this parameter in order to see the results. The next one is the quality level equals 0.3. And as the name suggests, it is the quality of the corners that will be detected. When the algorithm runs, it will detect 100 corners. But not all corners will be used during the execution of the algorithm, because we will filter only the best corners that were detected, and the quality level will filter the corners to track only the best ones. When the algorithm runs, each one of the corners will have a score. The higher the score, the better is the quality of the corner that was detected. And the algorithm will use the best score to filter the others. Let's suppose that the best corner has the score 1500. Then we can multiply the best corner by the quality level, 1500 times 0.3. The result is 450. So it means that the corners which have this score less than 450 will be discarded. They won't be used in the execution of the algorithm. The algorithm will start with 100 corners, but a filter will be applied according to the quality level. Let's suppose that 20 corners have the score less than 450. All these 20 corners will be discarded, so we will keep only 80 corners in order to execute all the algorithm until the end of the video. And the last parameter is the mean distance. It will be equal to 7. We can open this people image here, and this parameter will respect a distance of 7 units or 7 pixels, considering points that are close to each other. For example, a corner may be detected in this part of the image where I am pointing the mouse, and the next corner must be detected 7 pixels to the left, to the right, up or down. It is the distance of the closest edge. So there must be a distance of 7 pixels between the detected edges. And we are using number 7 because it is recommended on the documentation of OpenCV. Now, Let's create another variable, parameters, Lucas Canate, another dictionary. And as we can see here on the intuition slide, we are defining the parameters considering the KLT method, which uses the concept of pyramids. The first parameter, win size, equals 50 by 50, which indicates the size of the pyramids. For example, we can multiply 15 times 15. The result is 225. It means that the minimum size of the pyramid will be 225 pixels. And again, this is a default parameter extracted from the documentation of OpenCV. The next one, max level equals 2. It is the levels of the pyramids in this image that are 1, 2, 3, 4 levels, and we are defining a pyramid with only 2 levels. And the last one, criteria equals, and now we are going to use the same parameters we used for the other algorithms. CV2, term, criteria, EPS, and CV2, term, criteria, count. Now let's specify the values, 10 and 0.03. Both parameters will be used to indicate when the algorithm will finish the execution. Just a reminder that the first parameter is how many times the algorithm will run. If you set a higher number here, the algorithm will take a longer time to execute, but the results may be better. And regarding the second parameter, it will indicate how sensible the algorithm is related to the changes of the object. For example, if in the current frame the object is close to the camera and in the next frame the object is far from the camera. If you set higher values here, the algorithm will have difficulty in tracking the object when it quickly changes its position. And if you set a small value, the algorithm can detect changes easily. So you may try this parameter according to the type of video that you are working with. Let's create the colors variable, np.random randint. We are going to generate values from 0 to 255, which is the range of the RGB formats. And as we are going to detect 100 corners in the first frame of the video, we are going to generate 100 random numbers. And when we are working with the RGB color space, there are 3 channels. One channel for R, one channel for G, and one channel for B. For this reason, we need to put number 3 here. So, we are going to generate random numbers, 100 rows, and 3 colors. We can take a look at this variable. Let's print np.shape colors. Run this code. Let's just correct here. Video capture. Run again. Another typo here. Randint. We can see that a matrix was generated. 100 rows and 3 columns. We can also print this variable, print colors, run again, and we can see here the random colors that were generated. because each one of the detected corners will have a different random color, so it will be easier to see the results. Let's put both codes in comments, and I will create OK variable and also the first frame of the video, cap.read. This code here is just loading the video, while this other one is copying to the frame variable the first frame of the video. Now we need to convert this frame to grayscale, because it is recommended for this algorithm to convert the RGB image to a grayscale image, so the processing will be faster. I will create frame gray variable, frame gray init, which means the first frame of the video, cv2.cvt color. Let's put here the frame, the original one, in the RGB format, cv2 color BGR to gray. We can also take a look at the first frame, cv2 IMShow, the title of the window, init frame, and let's put here frame gray init, cv2 weight key and 0 here. Let's run this code. We can take a look at this window. This is the initial frame, the first frame of the video, and now the goal is to use the optical flow algorithm to detect the borders and the corners of this initial frame. After detecting the corners, then we will go through each one of the frames of the video in order to track each one of the corners that were detected. Now let's move on to the last part of this lecture. I will create edges variable, cv2, and there is a function from OpenCV which is called good features to track, and let's send as parameter the initial frame, the other parameter mask equals none. Later we will see more details about the mask, and the last parameter we need to send here parameters Shitomase. We have max corners, the quality level, and the minimum distance. So this is the initialization of the algorithm. We set the parameters, we send the initial frame of the video, and as a result, we will get the corners or the edges that were detected by the algorithm. This first part of the calculation will be done to detect the corners. Just a reminder that the Harris corner detector is being used. Now we can print length edges just to see how many edges were detected. 38 edges. If we try to use another video, for example, the race.mp4, let's change here and run this code again, see that 100 corners were detected according to this parameter here. And let's change again to the walking video. Only 38 corners were detected because the quality of the other corners that were detected were not so good according to the quality level. So we can conclude that the corners detected in the race video were better than the corners detected on the walking video. And you can try to change this parameter. For example, 0.1. Let's run again. See that when we decrease the quality, we get more points to track. I will keep that same value 0.3, and after we see the results, you can try to play with this parameter in order to see more or less corners. Now we can print the edges just to see the values. Run this code again. Take a look that we have 38 points, and the first value means the x-axis and the second value means the y-axis. In short, both values are related to the position of the corners that were detected in the first frame of the video. In the next lecture, we will use all these 38 edges to start our algorithm. They will be the initialization of the algorithm, and then we will see if we can continue tracking all these points. We need one more variable, mask, which will be equal to np zeros like, and I will specify here the frame. We can print np dot shape mask. Let's run this code. Take a look here that these are the dimensions of the first frame of the video, the width, the height, and the number of channels. As we have a RGB video, there are 3 channels, 1 channel for each one of the colors. And we can also print the mask. Run this code. See that we have a matrix composed of only zeros. When we are working with the RGB formats, value 0 is related to the black color, while value 255 is related to the yellow color. Later on, we are going to use the mask variable so it will be easier to understand. And in the next lecture, we are going through each one of the frames of the video in order to track the initial corners that were detected. See you there! Hello and welcome to this lecture, where we are going to finish the implementation of the optical flow sparse algorithm. Just a reminder that last lecture we defined the parameters. We are using parameters Shito-MASI, and then we are sending the parameters to this function good features to track, and we are also sending the first frame of the video. The algorithm will detect 38 corners or 38 points. We can see here the position of the points, the x and y axis. The tracking will start by these points here, where we are going to go through each one of the frames of the video. Let's implement the while loop, OK, and frame cap.read. We are reading each frame of the video. Now we need to convert the frame to grayscale. Let's create the new variable frame gray, CV2, CVT, color. Let's send the original frame in the RGB format, and let's convert color BGR to gray. This is the same code we implemented here, and we also saw the results. Now I will create 3 new variables: new edges, status, and errors. They will be equal to CV2. Now I will call the optical flow algorithm. We can use the function calc optical flow PYRLK, which means the KLT method, the Canet, Lucas, and Tomasi. That's mathematical calculations that will use the concepts of pyramids. So it's important to emphasize that in the first part of the algorithm, we only get the corners, the initial corners. And now we are using this method in order to reduce the size of the image using the concept of pyramids, and these parts of the algorithm that will track the objects. Just a reminder, we can assume that this part here is the current frame and the right part is the next frame of the video. The letters LK means Lucas Canade. And now we need to specify some parameters. The first one is frame gray init, the first frame of the video. Just a reminder that we are extracting the initial edges from this frame here. The next parameter is frame gray, the current frame. So the calculations can be done using both frames, the current and the initial. We are simulating this calculation between the images here, the pyramid. We also need to send the edges that were found in the first frame of the video. None is a parameter related to the mask. We are not going to use it. And finally, let's send here parameter Lucas Canade. This variable we defined here with the size of the window and also with the level or the number of layers in the pyramid. We can open the single tracking file. Just a reminder that we first initialize the algorithm, and then after each one of the frames, we get a new bounding box calling the update function. This part is quite similar. First, we get the initial edges, and this function will perform the calculations in order to track or to update the points. Take a look here that we are sending the initial edges that were found in the first frame of the video. And then, in this variable, new edges, we will get the next position of the objects or the next position of the edges. In short, we are updating the positions. This variable will control if we can keep track the object. It will return 1 if the algorithm can continue tracking the object, and 0 indicates that the algorithm cannot track the object anymore. And we can also see some error messages. We are not going to use this variable. Let's create the news variable, which will be equal to new edges, the new X and Y position of each one of the corners, and we need to get the ones with status equals 1. So it means we can keep tracking the edge. Let's create the odds variable, which will be equal to edges, also status equals 1. Both variables are used to simulate this part here. We can consider that old is this variable, the previous position of the edge, and new is this part here, the next position of the edge. So then we can apply the optical flow calculations in order to find U and V values that will indicate the next direction of the corner or the next direction of the object. As there are 38 points considering this frame, we need to go through each one of these points to visualize the results, because this while loop is going through each one of the frames, and we are tracking 38 objects or 38 corners in each one of the frames. So we need to implement another loop here. For I, new and old, two variables I'm creating now, in, enumerate, and now we need to go through news and olds variable, each one of the 38 values to each one of these variables here. As we are accessing two variables in the for loop, we need to add this code here, zip news and olds, so we can get the values of both variables at the same for loop. Let's get the points. AB equals new.ravel. This code is used to convert a matrix into a vector. Let's create C and D points, olds.ravel. Variable A and B will store the new value or the new position of the corner. On the other hand, C and D variables will store the previous position of the corner. Let's create another variable, mask CV2 line mask. Let's send here A and B, the new position, C and D, the previous position. Let's access colors in position I. When we use enumerate function, we are going to copy to the I variable the current execution of the for loop. For example, in the first time we run this for loop, variable I will be equal to 0, then it will be equal to 1, 2, 3, and so on. And we are going to use this variable to access this list of colors. Just a reminder that we are initializing random colors in order to print each one of the corners with a different color. And in this variable mask, we just need to convert to the list format and the size of the line. In some minutes, we are going to see the results of this function, but in short, it will draw a line to follow the object, similar to this one here, so we can see where the object is moving. Let's access the frame CV2.circle. Let's draw a circle in each one of the points. Frame, position A and B, 5 is the size, colors, position I to list, and the thickness of the circle -1. After processing the points and drawing the results in the video, I will create a new variable image CV2.add frame and mask, and then CV2 I am show the title of the window, Optical flow, sparse, and let's put here img, the new variable. This is an OpenCV code to keep the results of both variables in the same window. So we are adding them. Instead of using to imshow, we can add both windows to show both results, the line and the circle. If CV2 weight key 1 equals 13, it means the enter button in the keyboard, then we will break the execution. And finally, frame gray init equals frame gray dot copy. This is a very important code because at the first execution, we are using the first frame of the video to initialize the algorithm. However, when we keep processing the video, we need to compare the previous frame with the next frame. So we need to keep updating this variable. At the first execution, we will get here the first frame of the video. But when we go through to the second, to the third, to the fourth frame of the video, we need to update using the frame gray. So in the second execution of the for loop, the frame gray init will be equal to the previous frame, and we will compare it with the current frame of the video, always making this pyramid calculation. The previous and the current, the previous and the current. And finally, we also need to update edges variable, because take a look here that we have the initial position of the corners, and we need to update according to the new position, similar to this concept here, the frame gray init. So now we can just put here news, and in order to have in the correct format, let's type reshape -1, 1, and 2, just to put in the correct format to send to the optical flow function here. And after the while loop, CV2 destroy all windows and cap.release to release memory. Now let's run the code and perform the first test. And we can see one error here in the line function. And it happens on the line and also in the circle function, because these A, B, C, and D are floats, and we need to convert to integers. So we just need to type int, A int, B int, C int, D, and here int A and int B. Now we can run the code again, we can open the window, and we can see our results. We can take a look at a lot of corners that were detected. Some of them are not moving, like these ones in the car and in some parts of the grass here. And there is no problem about it, because as we discussed before, the goal of this implementation is to detect the 38 corners in the first frame of the video, and then we can track them. We could see that some of the points were related to people moving, so we could draw that line tracking all the movement of the person during the entire video. And when the processing of the video ends, you may see one error here at the console, and it is happening in this line here when we are trying to convert the frame to grayscale. And it happens because it's missing an important code here. If not okay, if we are not able to read the frame, then we can just break this while loop to stop executing. We can try to run this code again, just to make sure that this error is not being returned anymore. After processing the frames, the error is not appearing. So now our code is okay. And we can take a look at this part here. Just a reminder that we are adding the frame and also the mask. Instead of showing img, the new variable, we can just show the original frame. Let's run the code again, and we can see only the corners, the circles. It is related to this implementation here. We are detecting the points or the corners and we are drawing the circle together with the object. We can also take a look at the mask. Just a reminder that this variable is composed of only zeros, which are related to the black color. Let's run the code again, and we can see a very interesting visualization. We can see the lines according to the movement of the objects, and see these other points here with no movement. And to combine both of them, we can use the image, run this code again, and we can see the corners and also the lines according to the movement of the objects. And that's all for this first implementation. And in the next lecture, we are going to select the object that we want to track instead of generating the edges according to the algorithm. See you there! Hello and welcome to this lecture, where we are going to implement another example using optical flow sparse. In the last implementation, we just initialized the algorithm with the corners that were detected in the first frame of the video. And now the goal is to select the initial corner. So we will be able to select the object we want to track, and we will implement it using the webcam. We already have this optical flow sparse 2 file already implemented with this initial code. We are importing OpenCV, NumPy, connecting to the webcam, and then we are reading the first frame of the video and converting it to grayscale. Also are defining the parameters regarding look cascade. Just to recap these two first parameters, the win size means the pixels of the pyramids, and max level means that the pyramid has 4 layers. And we are using the same parameters as before, EPS and count. Now we will define a new function, so we will be able to select a point when the webcam is open. Let's create select point. It will receive as a parameter the event, X and Y coordinates, flags, and also params. And this is an OpenCV function that we are going to execute. Let's define some global variables so they can be accessed during all the execution of the program. Point, selected point, and also old points. If the event equals CV2, and we can type here event L button down, it means that we are clicking the left button of the mouse. It is a kind of a trigger. When we press the left button of the mouse, the code that we are going to implement now will be executed. Point will be equal to X and Y. It means the coordinates on the screen that are coming from these parameters here. When we click in a specific position of the window, the coordinates will be copied to this variable here. So the selected point will be equal to true. So it means that a point or a coordinate was selected. Let's access old points variable np array. Let's convert to these formats. X, Y, and the type will be equal to float32. In short, we will keep the current points and also the previous points. This is the only implementation regarding this function, And now we need to associate it with the window. Let's type here CV2 named window, and the name of the window that we are going to create will be frame. CV2 set mouse callback, and let's type here frame, the name of the window, and select point, the name of the function. So we are associating this function to this window called frame. Every time we create a window with this name, it will be possible to execute this function to get the points according to the left button down event on the mouse. Now I will create the selected point variable equals false. It means that no point was selected. See that the variable has the same name as defined here. So it means that we are accessing the same variable since it is a global variable. Let's create the point variable with the same name, an empty variable at the beginning, and old points will be equal to NP array empty points. We are just initializing the variable, and we are going to change the values when we run this function. Let's create the mask variable NP zeros like frame, the same variable we had defined earlier. Now I will just paste the code because it is quite similar to the one we implemented before. Take a look here that we are going through each one of the frames. We are reading the frame. If we can't read the next frame, we interrupt the execution, convert to grayscale, and the only difference is that we are checking the value of this variable here that is initialized with false, and when we click with the left button of the mouse, the value changes to true. So it means that a point was selected. And if a point was selected, then we run all the code we implemented before. We draw a circle on the points, we get the new points. This code is updating the location of the points. We send here the Lucas Canade parameters. We make a copy of the frame, store the old points. Here we get the current and the next location. We create the mask, the frame, and here we are adding the frame and the mask. The same code we had before. Here we have another difference. Key number 27 means the ask key. So when we press ask, the execution will be interrupted. Let's run this code. We can see one error. CV2 has no attribute name window because we need to change here to named window. And also let's change here callback with lowercase letter. Now we can run this code. Let's open the window. To test the algorithm, I will use the pen again. Then you can click with the left button of the mouse. Take a look that a point was generated. And now we can start tracking the object. The interesting point is that this line is generated according to the movement of the pen. When I put the pen in front of my face, the algorithm continues tracking. And if you click again with the left button, a new point will be generated so you can track the new object. And here we are showing IMG, which is the combination of the frame and the mask. We can uncomment this code to show only the mask. Let's run the code again. There are two windows. Let's select the point and track the object. we can see here only the lines that are generating according to the movements of the pen. So it is an interesting view to see the routes that the object is going. And that's all for this lecture about optical flow sparse. In the next one, you are going to learn the basic intuition and mainly the differences between optical flow sparse and optical flow dense. And right after, we are going to move back to the implementations. See you there! Hello and welcome to this lecture, where you are going to learn the basic intuition about another type of the optical flow algorithm, which is the dense, as you can read here. The one you learned before was the optical flow sparse. All mathematical concepts and calculations, especially the concept of pyramids, are the same, and we will only see what is different. The main difference is that sparse optical flow detects the corners only in the first frame, while dense uses the full image. Therefore, it is slower but generally gives better results. In short, in the sparse algorithm, the corners are detected only in the initial frame, and these same corners are used during the entire execution, while in the dense algorithm, the corners are detected frame by frame. There are several ways to implement this algorithm, and the one that OpenCV uses is the Fenerbach method, which uses a linear algebra concept called polynomial expansion. We will see more detail about this name here in the implementations. To understand the differences between the two techniques, sparse and dense, we can look at this image. On the left is sparse, and on the right is dense. As we can see and implemented before, sparse gets a few pixels that represent the edges and corners of the image, and then it is possible to draw a line that indicates the path of the object, which is nothing more than tracking. Something important is that generally the object is not selected. On the other hand, the dense algorithm lets you select the entire object. As you can see here, it's possible to see the shape of the cars. Earlier, I commented that the quality could be better, and we can see that the sparse cannot track this yellow car here, whereas the dense algorithm can, as you can see here where I am pointing the mouse. The color is more intense for objects close to the camera, for example, for this car here, and less intense for objects far from the camera, here on the bridge. If the object is not moving, it is not detected. The sparse algorithm is tracking here the edge of the road. On the other hand, here the image is black, indicating that the edge of the road will not be tracked. And that's all for the basic differences between the algorithms. In the next lecture, we are going to implement it using OpenCV. See you there! Hello and welcome to this lecture, where we are going to implement optical flow dense algorithm. We have this code with some implementations. First, we are importing OpenCV and NumPy. Then, we are loading the walking video in this folder here. We get the first frame of the video. Then, we are converting the first frame to grayscale. After that, we create the HSV matrix, which will be composed of zeros, and we are sending the first frame. So it means that we want to generate a matrix with the same size of the first frame. Just a reminder that the optical flow algorithm uses the HSV color space. Let's run this code and check these prints. The first one, we are printing the dimensions of the first frame of the walking video. Take a look here that we can see the dimensions and the number of channels. And then we are printing the dimensions of the HSV matrix that we generated here. We can see that it has the same size since we are going to use it later to print the results in the video. We can see here the first frame with the original pixels of the image from 0 to 255. We can also print HSV. Let's run this code again, and we can take a look that we have only zeros, which means the black color. Let's put all these prints in comments. Now we are going to access HSV matrix. I will put 3 dots here because, as we can see, there are 3 dimensions and we need to access position number 1, and the value will be 255. As we know, the HSV color space has 3 values. The hue, letter H, which is used to indicate the direction of the pixels, and it is position number 0. Then we have the saturation, letter S, that is used to indicate the speed of the pixels, which is position number 1, and the value is position number 2. When we type this code referring to position number 1, it means that we are changing the value of the saturation. So the saturation is initialized with the maximum value, which means the maximum intensity. We can print again HSV matrix, run this code again, and we can see that we have changed only position number 1. Position 0 keeps 0. Position 2 also keeps with value 0. We have changed only the saturation, which is position number 1. Now let's implement the while loop to go through each one of the frames. OK, frame equal cap.reads to read the next frame of the video. Let's convert the current frame to grayscale. CV2, CVT color. Let's send the frame that was read from the webcam. CV2 color BGR to gray. And then let's create a new variable. I will call it as flow. I will use an OpenCV function. Calc optical flow farne back. As you learned in the intuition lecture, there are some ways to implement optical flow dance, and the one that OpenCV uses is the Fenerbach equation. So we are using this implementation. If you want to know more details about the parameters that we are going to set now, you can follow this documentation link from OpenCV. The first parameter is frame gray init, the first frame of the video, and then we need to compare to frame gray, which is the current frame. We can take a look at the documentation here, see that we are sending the previous frame, and the next frame. And it is needed because of all calculations regarding the pyramids that you learned before. The next parameter is flow, and we will set it as none, and we will have a value for this parameter when there is a predefined direction of the arrows, and it is needed another output array, and as we don't have this other array, we can set it as none. The next parameter will be 0.5, and it is related to the scale of the pyramids. We can take a look at the documentation here, and the default value is 0.5, which means a classical pyramid, where each next layer is twice smaller than the previous one. Let's suppose the size of one layer is 30 pixels, and the size of the other layer will be twice smaller. So the size will be equal to 10 pixels. And then the next layer, the size will be about 3 pixels. The next parameter, 3, which means the levels of the pyramids. For example, in this image, there are 4 levels, and we are defining a pyramid with 3 levels. The next parameter, 15, which is related to the window size, regarding the number of pixels in the layers. And we will keep 15, which is the default value. The next parameter, number 3, which is the number of iterations the algorithm does at each pyramid level. In other words, it is the number of repetitions or calculations in each level. The next parameter equals 5, which is related to the concept of polynomial expansion, because the dense optical flow uses this mathematical equation. And in other words, it is the size of the pixel neighborhoods used to find the polynomial expansion in each pixel. And you can see the recommendations for this parameter. Typically, poly n equals 5 or equals 7. As you can see, we are using the default parameters. The next one, 1.2, that means the poly sigma, which is the standard deviation, and there is this recommendation here. If poly n equals 5, we can set poly sigma 1.1, and if poly n equals 7, then we can try 1.5. We can just change to 1.1 here, and the last parameter equals 0, which means the flags, and we are using this first option here. It will use the input flow, the initial frame, as initial flow approximation. It means that we are using the first frame of the video. After setting the parameters, now we need to perform some additional calculations. I will create 2 new variables, the magnitude and the angle, which will be equal to cv2.cards2polar. This is an OpenCV function to get both values here, to know the direction of the arrows, to predict where the object is going or the direction. And we will send here as parameter flow. We will put 3 dots here again, position 0, and flow, again 3 dots, because we have a 3-dimension matrix, position 1. In short, both values represent the x and y axis, the position of the object. We can open the optical flow sparse, and we can take a look at this variable here, new edges, which is the new position of the corner. And this code is similar. The result of this function will be in this flow variable here. So in the first position, we get the magnitude, and in the second position, we get the angle, which in short are the x and y axes. Now we need to access our HSV matrix, and now I will access position 0. We already know that in position number 1 is the saturation that we initialized with the maximum value, 255. Now we are going to access the hue, which is used to indicate the direction of the pixels, or that arrow, if the arrow is pointing to the left, to the right, and so on. And it will be equal to the angle times 180 divided by np dot pi. This is the pi number used in calculus, and let's divide by 2. Don't worry about all these calculations, because it is an algebra equation to find the direction of the arrow. It deals with degrees. And now we need to access the value which is in position number 2, which is the intensity of the pixel. And we will call the function normalize. Let's send here the magnitude, none, the second parameter, the interval. The values are from 0 to 255, and CV2 norm min max. Basically, in position number 2, we are just normalizing the magnitude. Now I will create another variable, frame RGB, which will be equal to CV2, CVT color, HSV, and let's convert from HSV to BGR, because we have this color space in the HCV matrix, which is used to perform the calculations regarding the optical flow algorithm. But in order to see the results on the screen, we need to convert again to RGB. And now we can show the result. CV2, I am show, the title of the window, dense optical flow, frame RGB. If CV2 weight key equals 13, if we press enter, then we will break the execution. And finally, we need to update frame gray init equals frame gray, because we always need to compare the previous frame with the next frame. At the end, cap.release CV2 destroy all windows to release the memory. Just an additional code here. If not okay, then we can break the execution. Now let's run this code. We can open the window and take a look here that this is a different way to track the objects. We are running the walking video, which presents people walking on that street. So we can see the color spaces here with information about the people. We can see that we have good results. We can track each one of the people in this video. And that's all about the implementation of optical flow dense. See you next time. Congratulations for completing this course on object tracking using Python and OpenCV. In this last lecture, I will quickly recap all the content that was covered. You learned the basic intuition of these 12 algorithms, and then we implemented them using OpenCV library. Until Goturn algorithm, we can see the most basic algorithms that we have implemented in the same source code, while the others, Meanshift, CAMShift, and Optical flow, are a little more complex regarding theory and practice. It is important to know the basic intuition of each one because you can know their main features to choose the best ones for the type of application you are developing. I really hope you enjoyed the course and feel more comfortable to take advanced course on this subject, since this is a course for beginners. Thank you and see you in the next course.